related courses. I'm also involved in Gilo. It's a startup. Well, with 4 people we have it now. It's called Garbage In, Logic Out. And with this, we help students and business people to help write their thesis. Well, mainly in the field of business, because that's where expertise lays. But we want to branch out to other fields too, including medical. Would be interesting since they have so many terms and complex taxonomies. Okay, be it as it may, we're going to do NLP. NLP with state-of-the-art models. NLP is natural language processing. It's basically, we want to try to have the computer understand human language. It sounds a lot easier than it's done, because there's so much nuance in human language. You can have, for example, references. I can reference, oh yeah, we meet at the same place like last month. Like, a computer can't make anything of that. Or like vague terms, you could say, oh yeah, I drove my Mustang there. Like, is this a Western where a cowboy sits on a horse, rides the prairie? Or is that a guy who has a Ford Mustang and drove well to his work with it? So, well, it's the nuances, it's the ambiguity, unambiguous aspects of it. I guess we'll delve into that. So the first things we like to know, NLP, natural language processor. It's kind of 2 fields that are very related, but not the same. NLP is really what I do. You look at the words as if they're statistics. So you kind of look at the total collection of words and try to make decisions based on that. It's often intended with machine learning, with deep learning, or with taxonomies where you have thousands of words. It becomes kind of, well, a collection of words you try to work with. Well, computational linguistics, it's kind of the opposite approach. It's more of a bottom-up approach. You look at rules of grammar, you look at rules of language, you try to make scripts that, well, that look at all the finer detail of every word. You want to know if a word, if a verb has the right inflection, or whether a noun and a verb matches. If one is plural, so should the other. So it's kind of a different, well, state of mind also, where NLP, it's very mathematical based, while computational linguistics is much more from the language side. It's kind of a left side, right side of the brain usage. They do make a good match. I have a computational linguistics at Gilo, who happens to sit here, my wife, Maha. She's very passionate about the rules of grammar and about every little detail. Well, I must say I don't know the rules of grammar that well, to be honest. I'm more looking at the meaning of text, the semantics, or what clause is the text in, or what can we do with the words. Finally, you have, of course, machine learning and deep learning. I guess they come in with NLP. It's a lot of things with NLP. Some you can simply claim, well, a word is a word, you can do something with it, but often it becomes unclear. For example, spell checker versus grammar checker. A spell checker would simply take a word and compare it to all words in a dictionary, and if it doesn't find it, it just tries the closest match. So that would kind of be a computational linguistic approach. While grammar as a whole, it becomes much more complex. For example, think of the word to in English. I wanted to go to New York, but airline prices were too expensive. The last too expensive is with 2 O's. The first 2 are with 1 O, and that's not even the word to as T-W-O. It becomes kind of impossible to fit it in rules of computational linguistics. You need an AI model that is trained with many of these kind of sentences and labels them. In this case, it's a homophone. If it's 1 O or 2 O, it sounds the same, yet it has a different meaning. That's a good example, but the difference between computational linguistics and NLP. So what can we use it for? Well, there are many applications. Here we see the spam filter, for example. Now, I can imagine a lot of the students, they're, well, from an age that you never emailed without a spam filter. But for the older people, you probably recognize this. Who remembers the Nigerian prince, for example? I always got mails from a Nigerian prince who claimed to go into a rough patch, but he has a lot of money he needs to transfer, and somehow his bank account got locked out. So if I can just give him the details of my bank account, he can use that bank account to transfer his millions, and you get 10% of the cut. I mean, how awesome is that? Apparently, well, back then people actually fell for that, and they wired the details of their bank accounts, which probably, well, I don't know if they even went to Nigeria, but definitely not to a prince. Another one that you might remember, apparently in the 90s people had a lot of, well, problems, well, from a sexual nature. So there was a lot of pharmaceuticals advertised to that, Viagra and such. Be it as it may, now we got a spam filter. Google Mail, Gmail, for example, is an excellent one. It just looks at your mail, it scans through the words, and through a deep learning algorithm, it knows this is spam, this is an honest email, so you never get bothered by all the spam. But it used to be, if you open your e-box, that it could be that like 75% of all your emails were spam. It's really annoying. Another one, translation, that is actually the original one for NLP. This is how the whole field gets started. People want to translate stuff without always hiring a translator, which is of course pricey and takes time. What else do we got? Auto-suggest also works great. In Google, you type a few characters and out comes all the things people, well, clicked on most or used most. You have your spell checker in Words or Grammarly. Maybe some people know that one. We also developed one in Gilo, where the spell checker is specifically aimed at business terms. And in that narrow field, we can do better than Grammarly. And here are a few more advanced ones. Chatbots. I guess you're all familiar with a chatbot. A lot of insurance companies, banks and whatnot, they have one at their website. And usually, well, if you go, you talk to a chatbot instead of to an actual person, unless your problem is complex, that you get transferred. It's a good improvement, because otherwise you pick up your phone, you dial, you're 20 minutes on hold, you get an operator who transfers you and then hangs up on you. No, chatbots aren't so bad, actually. In a similar, well, strain of thought, similar technology goes in digital voice assistants. You have your Alexa that can help you with simple things in the house. You have your Siri on your Apple. You have Cortina on Windows. I guess every big tech firm has one by now. We're going to talk about these two later. How do they do that? How does the computer start to understand what I mean? Finally, we come for the analytic parts. We have a large chunk of text and we want to make something of that. We don't want to read everything. There are companies who get millions of reviews or customer support complaints a year, and well, it's humanly impossible to read all that. So in the old days, just casually pick up a few random ones and hope that's good enough. But now we can do things like sentiment analysis, and we can conclude 78% of all our customers complained about a product. And then with text analytics, we can answer what is the product they complained about, or what sector was that in, what country was it in, etc. Funny thing, of course, it's all very dependent. Customer complaints depend so much on what does the customer expect. For example, we all know airlines, and well, customers are treated like cattle there. It's usually not a pleasant experience, yet hardly anybody complains about it, because I guess you imagine that's how it will be. Well, if you go to a very expensive restaurant and you're treated like a king there, you might still complain about it, because you imagined it would be even better. So it's kind of, well, relative. Finally, optical character recognition. It's basically scanning that whole pile of old papers we still have, and we want to keep the text intact. It's actually technically, I guess, a computer vision problem more than an NLP problem. The problem for us comes in play as NLP people. You scan it, and especially I went through it because I used a lot of research articles from professors in the field of finance, for example, but a lot of that being written in the 70s. And they said in a typewriter, they wrote that, then it's put to the archive for some decades, then somebody decides to scan it, and it's online, but the font is off, there are scanning errors. So you try to well, fix it. You have a table with common errors and how to fix them. I guess you can do an AI model. But it's harder than you think, good OCR. The problem plays a lot less in modern documents. If you have a thing that's written on your computer in a proper font, it almost, well, catches everything correctly. Well, now we come to the more computerized part of this, Python. And why is Python great for NLP? I personally, Python is all I talk. I don't know C# or Java or any of the others. I heard good things about them, but I don't know. For data scientists and NLP people, Python is really the only thing you want to use. There are several reasons. Python is pretty intuitively to learn. I tried C#, it's a lot harder. You have to type more, the commands are a bit more, well, not English, it's more technical. Because it's faster, some people complain Python is not that efficient, there is some truth in that. But it is easy, anybody can pick it up, I believe. Anybody can learn Python. The second one is Python is open source, and so are all its libraries. You basically don't have to pay a thing. I'm not sure all the libraries or most, but well, I use a lot of libraries. I've never paid for anything. So, well, there's no barrier of entry, so to say, in that perspective. Third one is you have a lot of things already that process text in Python, like you can split a sentence into tokens, or you can put capitalization in there or take it out. You can make dictionaries, you can make lists with words. It's all done sort of, well, by default, baked in the products. What else do we got? Yeah, the libraries we talked about. Well, AI specifically, although there are more ways to work with AI, I believe if you're serious with AI, you should either use TensorFlow or PyTorch. TensorFlow is a Google product. PyTorch is Facebook or Metaverse these days. Why these two? I guess they're the most developed. They're the most possibilities. It's also there are so many models to download for these two on GitHub or other sources. Often, like I know I use PyTorch mainly, but all the models, the BERT model we'll talk about later, you can just download it from the internet. To be honest, I never create a AI deep learning model from scratch. You just get something, try to tweak it to your own use, which is usually building your data pipeline and then have it running. I mean, who am I to compete with the inventor of BERT, who, well, probably knows more about it than I do, and he put this model there, well, open source, all easy access, free to use. Another one I like, Python has UTF-8 support. UTF, it's a text format, universal text format, I believe, off the top of my head. The thing is, it's 16-bit encoding, so you have all these strange characters with little umlauts, or the C with a little French hook underneath. It's a rich character set. If you use an 8-bit character set like ASCII, you always, well, the characters are changed, and usually in a weird way you get these OCR problems because of that often. The downside is, of course, if you have a string that includes like the O with little dots on it, let's say the name Muller. If I write Muller with a simple O and I write Muller with the O with umlauts on top, it is not the same string. It will be treated as two separate strings, which might be a problem in some applications. Then again, if you change some of the letters, if you all change it to, well, the simple A, the simple O, etc., you might run into trouble that the word with that special character is not the same as if you remove it. It's a different word. So it's one of those nuances of NLP. Well, what else do we got on this nice little plot? We talked about the AI part. Databases, it's quite easy. I use SQL Alchemy to connect to a Postgres database. It runs in Azure. It also runs on my local laptop because it's faster for development. It's really easy to access your data, your SQL data. You don't have to actually know that much about SQL, although I actually do know SQL. But you can write it, they say, at a Python way to approach the data, as in it becomes classes, there are functions. You can layer the functions with a dot, like select this, dot filter, dot order. Finally, pandas and NumPy are also, well, data manipulation, they call it here. It's basically pandas makes a, you could say, an Excel sheet, a table within Python. And it is really suited if you do calculations or changes on your data set as a whole. It's well, it's suited for that. It's fast, it works easy. Used a lot, and the same for NumPy. At the end, it's a linear algebra. It creates a matrix of, well, numbers usually that you feed into your AI, but we'll get into that later. Okay, the first module I like to discuss is spaCy. I'm not sure if anybody has experience or knowledge of spaCy. Yeah, there's 1, 2 hands. It's one I call state-of-the-art models. It's a very useful tool, especially for computational linguistics, but I use it a lot too for simple things like tokenization or analyzing your text after that. What does it do? They call it spaCy is industrial strength NLP. What do they mean by that? The algorithms have been tweaked really well, so it's fast. In the old days, I used, for example, regular expressions. Maybe some are familiar with those. The longer my text got, the slower they become. And the more keywords I wanted to look for, the slower it become. And at the end, it takes 20 seconds to, on a large text, to extract many keywords. The so-called industrial strength of spaCy, it does it a lot faster. They use C on the background. Most of the Python libraries are actually written in C to make it C++. It's an old language, but it makes it a lot faster. So it excels in processing large amounts of information, large amount of text information. And how does it do so? You can see here on the bottom, you get text, and it goes in the NLP pipeline. You do it with one command in spaCy. We'll get into that. There it does basically all the pre-processing of your text. It tokenizes the text, it separates the words, it tags it with certain labels, like every word is tagged as a noun or a verb or an adjective. It can do named entity recognition. For example, it can know, oh, Elon Musk is tagged as a person, or Rotterdam is tagged as a location. And finally, you can also run your own taxonomy, your own keywords through that. Let's tackle these one by one. So I don't want to go too deep in the coding itself. I give simple examples. You might try them on your computer if you want to after the presentation. It's also really easy to Google. There's so much material on this. Well, the websites like Towards Data Science or Medium.com are really good ones. Be it as it may, we start with tokenization. It's often the first process in the first step in any NLP process. And it basically means tokenization. In this case, means we take the words from a sentence and we separate them. Because now we got text like, I like NLP to do the work, but it doesn't walk my dog. Well, good points. It is just a series of characters. It's I, white space, L, I, key, and it's hard to analyze. You can use character strings on it. It's not very efficient. So we first want to tokenize that, and we do that with this little piece of code. We import spaCy in Python. Here we say the NLP spaCy load. It's kind of the pre-trained dictionary, and well, it's a data model. It's a miniature version of an AI model too. It holds a lot of knowledge, how to extract like people and places. What is a brand? What is this? What is that? Then we get our text and we say the document, the doc is NLP text. NLP is this preloaded spaCy model. The text is I like, but it doesn't walk the dog. And here the NLP part, it basically does this the NLP pipeline. It tokenizes, it tags, and it classifies the words. So if I then look in my document, there are certain labels. One of them is token. So we just iterate through all the tokens and out comes I as a token, like as a token, NLP as a token. It also tokenizes punctuations. You see a comma and a dot as separate units. Otherwise, it would be weird. Then it's dog dot as the last one, which is different from dog. And you might even want to do something with the punctuation if you write a specific application. Say that that's not a comma. There's no comma there. You can take it out. It is case sensitive, so NLP, upper or lower case, will be different strings. You can lower that if you want or not. Well, be it as it may. Oh yeah, here's another interesting one. Doesn't. It becomes does, and the other token is N apostrophe T, as in not. It's a good thing it does that, because doesn't, does not, the two words should be the same as doesn't, which simply represents does not. And it's easy to detect if it's does and N apostrophe T. And it would be much harder if it's kept as one word as doesn't. Same goes for can't or I'm or what else do you got? Haven't. A second neat trick it does, it's lemmatization. It's quite a word there, is it? The lemma means basically the root of a verb or the root of the words, the root meaning. So it converts every word to its root form. With verbs, it's easiest to explain. If you have verbs here, the things learn, learning, and learned have the same lemma. You can see what comes out. The toka learn, the lemma is learn, but also learning, the lemma is learn, and here we got learned, lemma is learn. That way we can compare sentences like in a chatbot. You don't want to be confused about different versions of the same verb. If you say I ordered, or I ordering, or I order, it should be the same verb, to process. Other lemmas, they're not available, like and, it just stays and, there's no other version of and, it's quite simple as that. Nouns can still have a lemma, as in the plural noun and the singular noun. Cars become car, or commodities become commodity. Also a useful thing if you want to extract keywords from your text, for example. If the disease in the medical file is in plural, while in your taxonomy is singular, it might not detect that. But with a bit of tweaking on this code, you can detect both the plural as the singular version of a noun. Then we got our, which one is this? Part of speech tagging. I kind of talked about this before. In goes sentence, I'm using Spacie. And then for every token, it says what kind of word is this. For example, I is a pronoun. Is an auxiliary, a helping verb. What we got? Using is a verb. Spacie is a
it's a proper name.
Well, you can look up these tags. There are, I believe, 20 of them that explains all that is to know about grammar and the type of words you use. Again, it's useful in, let's say, a chat bot. You need to know what are your nouns. You can often, remove or ignore things like auxiliary or proposition or helping something, but you need the nouns and the verbs. The nouns as in often I, who is doing it, I or you or me. A noun can be a place like Rotterdam, or an object like I want to order a laptop or a cheeseburger. So with this way we can tag all our tokens and know which one we should process and focus on and which one we should ignore. This Spacie is a helper tool for that. It's quite fun. It draws you a little diagram and your sentence goes in. The computer keeps crashing on my bad code. We can see exactly what word depends on what. For example, which is a big one, code. Can you maybe explain this? You want to give this a shot?
Sure. Okay, so first of all, the word crashing is misspelled, but I'm a pedantic person. So if you look at this, it will give you a determiner. Determiner could be the, a, and, could even be some. A noun, which is in this case the subject. So the verb is related to the noun subject, which goes from the verb to the noun. So this is qualifying it, goes to it. The same goes with another verb, because you've got a one verb in this instance. And a second, this one is what we call a gerund, and it then is related to, this verb is related to this verb. Is very complex. Now you've got here a prepositional phrase. So here, this batch is connected to each other. And so let's take this apart before we connect it. So we know in this instance, the noun here is the object of the prepositional phrase. So it's the object and the verb is related to the object, and the object is being done by the verb. So you've got the noun, in this case, object, and the adjective is related to it. This is why it points directly to its relationship. The same goes with the determiner, like I said, a, the, and, some, and the noun is related to the determiner, and the case is the prepositional phrase begins with the preposition, and adduct means add preposition, because in some languages it's not just a preposition, it's an add. It's very complex linguistic stuff.
Okay,
so yeah, and so it's related again to this whole phrase. So that's why it goes from the preposition to the object. So this is how it's very complex. You need to know linguistics to really do a complex thing and play around with the text.
I guess it fits well in a field that's relatively new. It's called conversational AI. It's basically managing chatbots and the conversational chatbots. But we'll get into that later. At least you know what a computational linguistics are up to now. Okay, then we got our named entity recognition, NER. Maybe some of you heard about this concept. It's basically we want to extract terms out of a sentence but we're not exactly sure what. We know the type, but we don't know the specifics. So it's not that I have a taxonomy where all diseases and medical terms are specified and please extract whatever's in there. It is things like I want to know people and places, I want to know amounts of money, or I want to know dates or telephone numbers, but I don't know really how to specify them. So this is the part of spaCy where it's trained on an underlying AI model, which I suspect is BERT. And this is also the part where it comes the so-called state-of-the-art model. The other, well, tools you have in Python to do these kind of things. I'm talking about GenSims, NLTK, and what was the other one? GloVe. We got several. They're not as sophisticated as this one. Well, let's see how it works. So if we in a text on the 21st of July, Elon Musk charged me $50,000 for Tesla that I then crashed in the center of Rotterdam. What can we extract from that? Think again, we're a chatbot or a virtual assistant. What are the key terms we need to know to work one? Well, we got, of course, there the 21st of July. That's not a token, that's a span of tokens, since there are actually 1, 2, 3, 4 of them in a row. This span is labeled a date, so I can use that as a separate unit if my chatbot wants to know when did it happen? Oh, the 21st of July. There's something labeled date, so it's easy to work with. The second one, we find Elon Musk. That's a person, and I'm sure it's been trained on many persons. Maybe Elon Musk, since he's a famous guy, is literally in the data set that's exposed to the AI. But I've tried all kind of names, it works quite well. Erwin Lubbers, it detects too, and I'm pretty sure I wasn't exposed to the data set that trained the algorithm. Then this fellow, Elon, he charged me $50,000. 50,000 is labeled as money. It missed Tesla as a brand, that's peculiar, it should have picked up that one. And then finally, it knows Rotterdam as a location.
Oh, it didn't detect it because you're using the small rather than the large spaCy load.
Oh, good point. Here you see the NLP, it loads the pre-trained model of spaCy, and here the last thing is SM, which is, well, it's small. You also have the medium and the large one. It's a lot bigger. I believe the small one is less than 10 megabytes, the medium is 40, the large one is 700. So the large one, it knows a lot more about specifically this. It holds a much bigger AI model that's trained on more names, so it's much better at recognizing things like Tesla. Indeed, if you would lose the large corpus, it would detect Tesla, I'm sure.
And why would you still use a small one?
Because it's small. For example, I make my algorithms on Python. Somebody else makes an API, a programming interface of it, and you put that in Azure. Now Azure charges me for all kinds of things, every call or every storage unit or every processing amount. If I use the small one, the cost will be a lot lower. If I often have to load the 700 megabyte data set, my bill will be 10 times higher. So it's always a bit of tweaking. If you run it for research purposes on your own computer or it's limited in the cloud to only you, I would always use the large one indeed. But if it's for many users that all simultaneously fire up that thing, then you have to look at efficiency. But it's a good point, yes.
Another question, because it says 50,000, the token is money, but would it just see the 50,000 or would it also see the dollar sign?
It looks like a dollar sign too.
I would expect that too. That's probably another quirk of the small library.
Yeah.
I would expect it too with a dollar.
Yeah, the large corpus looks at money with the dollar sign, and otherwise it would label that 50,000 as accountable.
Yeah.
Countable number.
That's a good point because
Cardinal, sorry.
50,000 euros and $50,000 are not the same. It's a different number,
No,
really.
50,000 kilo or liters.
Yeah. So it labels as a cardinal account.
And you've got a little thing, Displacy again. It can also make a nice rendering of all the tags it found. So you can have your whole text through it. It labels exactly, oh, here I found a date, here I found a person. And it works really well, even on a large text. I tried my thesis. It's like 50 pages or something. Within a second or two, you got your whole thesis with everything highlighted of people, places, etc. We're getting now to the more practical uses. I think it's the first real example of something interesting. Chunking. It's a process probably not everybody's familiar with. Chunking, it collects nouns mainly, plus all their dependent words, kind of what we saw in this dependency graph. So think about a noun could be car, but a noun chunk would be the red race car, or the stock market crash, or it could be anything centered around that noun. Let's see what we got. The stock market crash of 2008 was caused by investment banks, real estate, and interest rate derivatives. So what does it get from there? The stock market. Unfortunately, not the stock market crash, but, well, it's a start. Oh, crash is a separate one. I guess it's not dependent on, well, investment banks, real estate, interest rates. Should be interest rate derivatives. Well, it's not perfect, but the idea is there. You kind of extract, instead of, a single word, you extract a set of words that relate to each other, that should be grouped together.
I know why there's a problem there.
Might be the small thing again.
It's a small thing, but it's also because they haven't trained it. Like we in Gylo train groups of words that already in advance. So we already know it's interest rate derivatives because we have as keywords set up. So we've already predefined it, but they haven't predefined it in the Spacy text. So they don't look at the chunk as one entity. So we've named entity that.
And it is a thing I can discuss briefly, but we go into it later. These models are often trained on a large corpus of text, but usually, quite generic text. Think about Wikipedia, think about Google News. It knows about a lot of things, but never that much in detail. While we, for example, we focus on the field of business, so we know all about business terms. If you ask medical terms, well, it will not give you great results. So it's kind of, are you broad or do you want to be specific? Anyway, what can we do with these chunks? Well, here's a little piece of code. I am not really going to go through it, but it opens my thesis as a text file. It uses the NLP pipeline on it, where it tokenizes, it does the chunking thing, among others, and it labels things. Then out comes all my word chunks, well, including stock is found 15 times, stock return 3 times, stock volatility 1 time, a lot of other things too. Now, if I do this on my thesis, well, I get very specific result. It's not that useful for an autofill, but I have 1,500 research articles for broad fields, not only business, but some are medical, some are psychology, some are IT, data science. So I let now this noun chunking mechanism go through all these 1,500 research articles, and you get a much broader, well, better understanding of the language that is used there. And with that, for example, we can use an autofill application. So again, we use noun chunking on 1,500 different research articles. We notice the frequency of the noun chunks that are used, and out comes something like this. For example, think about this as your user interface. I'm typing and I type FRE. I'm thinking, what do I want to say? Not just freedom, I want something more complex. On the background, you get an SQL query. This noun chunks with their frequency you all put in a database. I got main database, got about 150,000 noun chunks now because, well, they're much broader than just text. Dictionary, for example, is 30,000 words. But here, well, free has a lot of add-on dependency on it, so it gets quite big. It is a simple SQL query that looks for anything that starts with FRE and simply returns in order by the frequency it's found in my text corpus. And out comes something like this. First you get freedom because it's found 1,100 times, then free cash flow, well, we are a business tool after all, free trade, free markets, free will, free hold, free rider problem, etc. I can imagine this also must work as a gem for medical texts. The medical terms, they're extremely complex and, well, they can be a bit long. So it would work great if you just type the first few characters and out comes all your suggestions for whatever, well, the first characters match. And, well, these will be then put back in your user interface where it simply suggests for free. I would suggest freedom and all the other, well, depending on the order of you put it in. I guess it's also a thing with is AI biased or algorithm biased? Well, we get into that later too, but you can already see here where the problem might start. If I have certain text, in this case business text, well, you get free cash flow, freedom, free trade, all these things. If I only would use medical terms, it would give me a very different list. Now, these specifics, well, they're not really racist, sexist, or whatnot, but when I have a political science corpus, a sociology corpus, psychology, well, you can see that different results might get to, well, some people being offended, there can be problematic things. It is interesting to play around with, though, to discover why does the computer give me this, and why did it find that. It's usually a bias of the data set, I believe. Okay, well, we managed to get so far. Is it time for a break yet? What do you think? No, I should go a bit further. Okay, the next thing I like to talk to you about are taxonomies. And taxonomies, they're really a collection of words. A collection of words, in this case, keywords in the field of business. I give a definition, although that's not mandatory in taxonomy. What is mandatory is classification. So I say, for example, portfolio. What I mean here, it's in the field of finance, then it's assets, and then it's portfolio. I guess they're kind of cryptic labels I use for myself, but when you extract these terms, you can, well, make a whole diagram. You got so many finance terms. In finance, you wrote about asset management, or you wrote about the financial derivatives, or you wrote about the stock market and trading. Another thing, it's more a Gilo, what we do. We have definitions of all our keywords, also with the source, the academic source, because a lot of students, they have trouble They can find a keyword. Everybody can do so. We all have Google. You usually get directed to Wikipedia, which is often not acceptable as an academic source because you don't know who wrote Wikipedia. It might be an authority on the field. It usually is actually, but it might also be somebody who doesn't know his material that well, just some random guy who likes to write about it. So therefore, the student gets to hear, no, we can't accept Wikipedia. Then where do I get these scholarly definitions? Well, that's where one of the things Geilo does. We did the heavy lifting. We discovered all the correct terms and we classified them. Anyway, back to the taxonomy. We put our text in this case, my thesis again. It matches things, modern portfolio theory. It sees risk, it sees diversified, it sees investments, it sees basically all the keywords that I defined in my taxonomy. I can now get out of my text and put in a simple list for further analysis. You could even go as far. Bill Immen is one of the advisors of Geilo. He has an NLP company too, which specializes in extracting text. He calls it textual ETL, as in exchange, transform, and load. He extracts all the useful bits of text files, and he stores in SQL then the terms with the classification, and then, well, you can do analysis on it. As in, for example, customer complaints. What are they complaining about? For example, you have in your taxonomy, you have all menu items. You have pizza, you have hamburger, and whatnot. You can extract those. Then in another taxonomy, you have locations. And another one could be, well, anything that might be needed for that case. When you combine them all, you can come with conclusions like 70% of the complaints was about pizza and 50% complaints was about the location Rotterdam. And you might have to talk to the manager of Rotterdam and his pizzas. There's something wrong with it. I'm not even going to read the complaints or anything. I just, by the aggregates of it, I can already make my conclusions. Another interesting conclusion Bill found is prices. Sometimes you get information of people who don't complain that there's a lack of. For example, prices. People always complain the price is too high. They never complain the price is too low. If you never have complaints in your customer department that your prices are too high, your prices are too low. Otherwise, people would have complained. So it's time to raise prices. So these kinds of conclusions you can draw if you have a taxonomy and you have a handy mechanism to extract all your key terms. And I guess you can guess it already, it works really well with the named entity recognition. We discussed earlier that you know who is doing it, where, and how many, what, and then you have what exactly is it. SpaCy can help you there too. It's called the spaCy Matcher. The code becomes a bit more complex, but the basic idea is you get a word list. In this case, I just added a few simple words in a Python list. You should run your whole taxonomy, well, as a list. You add patterns. You can make patterns really elaborate in spaCy. It's not just the word goes in there and that's what you find, but you can, for example, you can add the lemma to it. So having and have, or commodity or commodities are treated the same. You can also add combinations. I want one keyword, then a hyphen or a comma, and then a second keyword, which is different than if the keywords have a white space in between or no space at all, like non-performing loans, or the loan is non-performing. It's written differently with or without a hyphen. Be it as it may, I have my keyword list. I run it to a text, in this case a simple text that I invest in the stock portfolio again, and out comes all the keywords I wanted to see. Invest, stock portfolio, risk and return. So if we make it a bit more difficult, here we see well, a small example of a medical taxonomy. In this case, the Harvard Health, it's online accessible. The beauty about a lot of these taxonomies, there is so much to find online. You can pay for them too, you can pay quite a lot, but you'll be surprised with a little bit of Googling how much information is publicly available. It's often through universities and research institutes that well, have a public function already funded by public money, so I guess they should publish these things without charging people for it. The same concept goes here. You get a text, you run it through your taxonomy, through the Spatie matcher, and out come all your keywords. And you can quickly see in the keywords alone, oh yeah, pneumonia, novel coronavirus, 2019 nCoV, laboratory. Well, this must be something about corona. Well, that is true. Although I'll show you after the break that our AI deep learning models were much better at classifying the text as a whole, saying this text is medical and it's specifically about corona. We use this mainly after the AI has classified a text as medical, then you run your medical taxonomy through it to extract the exact details. What disease is it exactly talking about? What treatment? Very interesting applications in it, in I guess every field, but medical is probably the most useful because you can make predictions. What is the risk of a patient developing dementia in 5 years based on his medical records? So the AI can flag this one is risky, this one is not, and then you have your taxonomies to extract why is it risky? Well, did he already have one of these symptoms? Did he already use one of these medicines? Did he already, well, something. So some people think, well, with deep learning and all the new techniques, taxonomy sounds really old-fashioned, but it's not. It's still a tool that is used in it, and if you have a serious application, you'll probably have a taxonomy. Well, here we got a little visual about what we can do with this text. This is what I do with Gylo. For example, I can count with my taxonomy of business terms all the keywords I find in your text. I then can classify them with the taxonomy. I know finance, I know marketing, I know HR, I know all the subfields of business. And under that, I have subfields and subjects. And then you can come up with a little tree map. Here's my thesis, for example. I wrote it for my Masters of Finance at Erasmus. And as you can see, the blue square are finance terms. So it's probably a good, it's never one, how to say, subject. There are always, you talk about economy, you talk about other things, data science maybe, or medical in a financial perspective. But roughly half of finance, that's great. Sometimes you run a thesis through it where accounting and business management and real estate are bigger than finance. So the student can start to worry. I'm writing a finance thesis here, not a real estate. Am I on the right track, or did I go off the path somewhere? And if you're interested in the details, you can always click, oh, I wrote this much about derivatives, future derivatives, or options, or whatnot. I wrote about, let's see, portfolio theory. I wrote about corporate valuation and whatnot. It kind of all makes sense, but you can imagine if a student just starts writing it, because this is the end product, which was, well, edited and everything and looked at very carefully. But if you start writing, it's often a mess. You've been there, you write and you write and you write, and after a few pages you think, I got off the track. So it's a great tool to analyze that. Then next to taxonomies are ontologies. The two are roughly the same, but an ontology is more complex, as in taxonomy uses a very simple classification. You already saw my taxonomy. You have the finance is the field, then the subfield is financial derivatives, and the subject could be futures or options. Well, here it's used in medical a lot. You can say the classes are, well, we end up with alcoholic cirrhosis of the liver, which is part of diseases of the liver, diseases of appendixes, diseases of the digestive system, etc. So you get a much bigger classification, but also one term can be classified in multiple areas, where in my taxonomy, one term is simply there, that's its field, its subject, etc. Here you can say, well, I don't really have good examples, but you can imagine that a certain disease or a certain body part or treatment might be both there and there. Or you can classify it better, like you have cars, then you have the Porsche is a type of car, then you have the 911 is a type of Porsche. But the 911 is also a type of car and also a type of whatever is on top of their transport system. So again, ontologies and taxonomies, they're roughly the same, but ontology adds more complexity to it. And in this case, it's an interesting bioportal. You have several others. They're also accessible for free, but you can only access to their website. So you can go here, you can Google bioportal, you'll end up here, and you can find any of their descriptions that you want. But in case to make this really work, we want the whole ontology and run it through our text, through our medical records. And of course, that's the moment where you have to pay, because it's kind of a freemium model. They give you certain hints. You can maybe, as a doctor, you can test if all your terms are there and if they're properly defined and classified. And once you're happy with that, you need the whole thing. And you pay quite handsomely for that. I was told they're not cheap.
You can get it from the university. I think that this university, for example, might have a relationship with a company that you can get access to the Excel sheet kind of setup. And then you can get all of the various ontology connections. But I mean, right now, if I was to do cirrhosis and I would want to figure out some relationships, it would be too complex. I mean, imagine if I want to do that relationship with a drug. I have to I can't do that because I only have that flat structure. I don't have the interrelations. But if you get the Excel sheet or a SQL database that has all the ontologies set up and linked together, you can find the interrelations.
Another interesting fact about medical ontology, or well, medical terms in general, they're extremely complex. And you might think my field is complex too, business or IT or any field could be complex with all the jargon, but medical really is on a league of its own here. For example, Bill Immen, well, he did a study to it. He came to the conclusion in an English dictionary, you got roughly speaking 30,000 words. You got most of it covered then. If you want a very, well, everything included dictionary, you get about 60,000 words. You get the very rare words included. My taxonomy on business terms, I have less than 20,000 business terms. I find it, well, I wouldn't say it's everything is included, but it definitely is a very, well, complex, and there's a lot of stuff in there for business. Medical, on the other hand, Bill estimated it to be 600,000 terms. I mean, it's such a ridiculous amount, and then you have to know which are synonyms for what. You know, you can understand that an alcoholic cirrhosis of the liver, there's probably a Latin term for that, and it's exactly the same, just a very different term. So yeah, again, the complexity in medical, it's just so much more than any other field. Let's also see why there's, well, the most work to be done there and why it can gain the most of NLP applications. If we can use all the medicals history, the electronic patient files, and we can, well, create useful information out of that, it would, I would say, add almost as much to healthcare as the invention of new treatments, new medicine and such.
And the beautiful thing is when you use the ontologies with the named entity recognition, you can look at synonyms. So like you can literally find another word for cirrhosis, and then you can find all these things. And if a person called cirrhosis by its acronym, you can do that too. And you can find the interrelations as well.
Okay, well, the last subject I'm doing before the break, in about 15 minutes, is word factors. Now, word factors, they're really fun. This is probably the most fun part of NLP. Oh yeah, that's 11?
Yeah.
Oh, that's soon on. I'll get there exactly. Okay, so first of all, what are word factors? With a word factor, you first tokenize your text, as in you make every word a token. That token becomes represented by a vector. And a vector is, well, you can see, you might imagine it's a little arrow pointing in a certain direction. It becomes a bit more abstract because here it's often a 100-dimensional vector. But that's basically a list as you see here with 100 numbers. And you can imagine it's a pointer pointing in some, well, theoretical 100-dimensional space. Don't worry about it too much, how it exactly works. The thing is, word becomes 100 numbers. Now, what are these 100 numbers? We get in the algorithm later, but it really represents the words, and the different numbers represent different elements of the words. And now words that have a very similar meaning, they have a very similar word vector. For example, king and queen are really close to each other. You might say, isn't king the opposite of queen? That is correct in a way, but that's only if you take sex as a standard. Then king is the opposite of queen. But actually king and queen, they're always mentioned in the same perspective. They're always, you could also say king and queen isn't peasant the opposite, because they're on top of the hierarchy and the peasant is at the bottom. Or maybe you can say president is the opposite, because the president is an elected official while they're monarchy. So different words get different vectors, but similar words get similar vectors, and then we can derive synonyms out of these. What's most related to a certain concept? Antonyms, I quickly told about. You might expect that antonym is the complete opposite of the word vector, but that's never the case. The antonym is also really close to the original word vector. Why? Because the antonym as king and queen is usually just a difference on one element of the words and not all elements. So the opposite word vector of king, you would get something completely related, like yellow or sunshine or something. Therefore, it doesn't know the difference between synonyms, antonyms, or just related words. It just gives you a list of words that are most similar according to the algorithm on an average of all the meaning of the words. And again, it can capture many different aspects. For example, if you would train the algorithm and you throw a bunch of articles on Rotterdam and probably some other cities. One of the things it picks up, Rotterdam and Amsterdam and The Hague and probably some other cities, they're really close together because they represent a city. But also Erasmus it picks up. Erasmus is always mentioned in the same context as Rotterdam, therefore it has a very close vector. Or you might think harbor might be another one. If you have some text in there that talks about the harbor of Rotterdam, it relates them.
So can I make a comment? If you look at like dictionary.com, or thesaurus.com, okay? And you'll often go, okay, well, you've got your synonyms, you've got your antonyms, and they'll sometimes show you word vectors, right? They'll think, oh yeah, well, they build word vectors too. Well, they don't necessarily use it. They use lookup tables because if you look at their data, it's always too perfect, meaning it doesn't do like the throwing in the Erasmus in as a kind of a word that really doesn't fit all the cities. So often you will know that if you use word vectors, you have to be very careful because you will always have tangential concepts because of the text that is being read by the Word2Vec system. So often thesaurus.com and dictionary.com or hippo.com, they will have already built in their system with the text or a lookup table to give you offer definitions. We at Gilo use a three-pronged approach. Could you explain how we use Word2Vec with synonyms, for example? And
yes, I first, in my own approach, I use a lookup table for I would call them hot terms, problematic terms. You can say if you, certain religious terms, if you say something, if Word2Vec or say something really, well, unexpected about that, could lead you in all kind of trouble. The same could be for politically correct language. We want to sell to academia, so you've got to be a bit careful in your, sociology terms, your political science terms. So for the things that are a hot debate, I have this manual lookup table where I just put a few synonyms in. If it can't find it in there, it starts to look at my Word2Vector model, which is for my business. It's not only business, also political science and some other related fields, articles. If it can't find it in that, or it's not properly defined, there's a pre-trained model of Word2Vec. It's a massive model. It contains 3 million words. And well, like yours said, weren't there only 60,000 words in the dictionary? It does include things like names and places, and not just New York, but maybe Schiedam is in there too. And, you can imagine with people and places and all kind of things, brands, it becomes much bigger. But I like my own corpus better as long as we talk about business terms. My corpus is simply much better at getting business terms because it's specifically trained on those business terms. While the generic Google term, it's based on Google News and Wikipedia and such. It's good at generic English, where my business thing is not good at. If you ask my model, give me a synonym for yellow, it probably comes up with really weird terms, while the Google pre-trained does handle that excellent.
So if you look at Microsoft, if you ever want to look for a synonym, antonym, you'll always notice it's like near perfect. Why? Because they use lookup tables. So the Word2Vec is really a cool thing to use and have, and Spacey has it too. They can actually test to see if your terms are similar. They also have an algorithm under the hood. But ultimately, if you're going to use word vectors ever, let's say you want to do it in finance, or if you want to do it in medical, you have to be very careful because you have to build in and connect it with a taxonomy, or make sure your text that you plowed in are related words that are, you think are truly related.
So how does Word2Vec know, well, what word relates to what? Well, first of all, nice quote. You shall know a word by the company it keeps. I believe at the original, you should know a character by the company it keeps, but it goes here quite well because it takes in sentences like I like natural language processing. It goes through every word. You can call it the window. So in this case, the window is on language. It kind of blocks that out, and now it looks at I like natural blank processing. Then it tries to predict the words, and well, then it unmasks, is it language? No, maybe you have to go back to a better prediction. And when it does that, then it goes to the next one. It tries to predict processing. You can do it the other way around too. You have your words, your target word language, and then you mask natural. You try to predict its context words. Well, two-way approach. This way you can start to see how the context will build. If I have the sentence, so it's not that the word is directly related to another word. No, it's the indirect relation of context. For example, Bob went to the bar and drank a lot of beer. We can say Bob is then the target words, and the context is bar and beer and drink. Then the other line, in a completely different document, it says Alan went to the bar, there he drank some beer. Then it also relates it to bar, beer, and drink. And therefore, Alan and Bob have a very similar word vector. It's not similar to drinking or bar. So it's the context, it's the indirect approach that builds these vectors. And well, oh look, we got our first neural network. Well, I'm going to keep it a bit simple because I can imagine it's not really a lecture.
Because it's too advanced.
Okay. I think some people are ready for a break. Should we do a 15-minute break and then we start, well, 15 minutes?
Yeah, everyone on that side too.
Yeah.
Okay.
Are there any questions for the people online? Okay. Oh, you're monitoring it. You are still awake, aren't you?
Yeah, I also have some really cool examples, but we won't have to do it for this. For if you want to do what Grammarly does, you do better. So we can kind of like, if you ever have questions about that, feel free to ask Erwin, and I will teach you how under the hood Grammarly does the things that they do. Because we basically broke Grammarly and put it together so we could be better than them. Remember, we deal with logic errors. So we go one step beyond grammar. So if you ever have questions about that and you're just curious, how the hell do they do that? Well, I can give you the answer.
It is, by the way, also a thing. The introduction, I already talked about state-of-the-art models, SOTA model, they call it. Why state-of-the-art? Well, Spacey has been really improved lately with their AI-related algorithms, and BERT, I get into that later. It's a manner to look at sentences. They're pretty recent. They're just around since 2019. So state of the art, it gives you the best results. They're new. It's a problem for companies who have old technology. They invested a lot of money and time and programming and energy in these old models. And they're not really keen on every 3 years getting the state of the art model, which gives you better results, but you cannot redo your whole code and your methods and your data every 3 years. So I guess it's good for Gylo. We enter here, we use state-of-the-art models, and hopefully we're better than the competitors. But I'm afraid in 3 year time, new models will pop up, and if we don't change everything again, then our competitors will eat our lunch.
Well, as an example, Erwin and I had built with our interns last semester the search engine. And the search engine, we based it on databases. And then Erwin and I were like, ooh, that's too old school. So we had to move everything to NER, not named entity recognition, along with auto suggest, because that's semantic search, and Erwin's gonna explain that. And we had to just change it all. We've changed so many things because they're like, wait a
Let's
minute,
take a break.
we've got it.
People online, coffee time.
We're taking the break now.
Have to change. Erwin and I studied the closer to his mic.
Yeah, yeah, of course, I will stand there, yes.
She's an ethics person, so we've got some fun ethics issues with AI.
Okay, well, everybody back already?
Hi, guys, is everyone there? Can you hear us?
I will turn everything on for you, I think.
Oh, please do.
Yeah, I put the video and the audio back on.
Oh, okay, and also microphone?
Yeah.
Yes, everything's on.
Okay, I don't hear anyone. Everyone's away from their computer. Maybe they're still silent. Okay, let us begin.
Okay, so where were we? We were with word to vector and word vectors. How does it calculate these vectors? I won't bore you with all the details, but some might be interested in the more technical aspects. First, you get an input vector. It's basically a one-hot encoding, which is, for example, my vocabulary is 30,000 words. I get 30,000 bytes there, which are either 1 or 0, and it simply says word number 1 in your vocabulary is 1 and then all 0. Word number 2 is 0, then 1 and the rest 0, etc. Then it goes into the hidden layer. There's one hidden layer without any activation function. It's really a simple neural network. And outcomes, the output layer, are the words that it suspects are there as the masked words with the probability. So it knows, and then it unmasks the word. It checks if the word is correct. It can go back, change something in the weights. At the end, if it's happy with with the probability of the outcome, it takes the weight on this layer, the weights from the input vector to the hidden layers. The hidden layers are the same length as your word vector. If I use 100-dimensional vectors, I got 100 neurons in my hidden layer and also 100 weights here, which should become the word vector. To be honest, it's all theory and I never use these things. It's nice to know, I guess, as a student, if you study these things, you'll get quizzed by it on an exam, but you'll never use it in practical terms. You do need to know how the thing actually works in practice and application. Okay, so how does it work? Well, we briefly talked about this already. We got word vectors here. For example, the king and the queen, it's the most debated on the internet with word vectors because it's so black and white, you could say. It's so yes or no. While with most language, it's much more gray. It's a probability. While here it's king and queen. It's bad and good. It's old and young. It's all these things. Anyway, king and queen, they're similar vectors because they've been mentioned in the same context often. But why not king and peasants? Because the king is on top of the hierarchy while the peasant is at the bottom of the hierarchy. That's another, relation or antonym in this case. Or the king and the president. The president, he's an elected state official, while the king is a monarchy. Lastly, maybe a bit far-fetched, I would say king and the silverback gorilla. Well, silverback is the leader of the group, so is the king. So they might have related factors, you never know. Thing is, AI, NLP doesn't know the actual words. It's always tokenized and then it's vectorized in a word vector or just a number. It just looks at numbers at the end. So don't imagine that the AI can actually read. It knows numbers as word representations, and out comes a number which I translate back to a word, and the AI kind of pretends it knows how to read. But anyway, back to our king and queen. As you can see here, prince and princess, they probably got a very similar closeness of their word vector. It's not the same as king and queen, but it's the same distance. As in the only thing that's different between prince and princess is their sex, and so is king and queen, and so is man and woman. Now here's the interesting thing. Once we change words to numbers, we can do math on it. We can do additions, subtractions, we can do all kinds of things. So it's the famous example is king minus queen plus woman is, king minus man plus woman is queen. Now what's going on there? Let's see. We got our king right here. We deduct man from it, so we get, I don't know, here somewhere, and we add woman. Where's that one? That. So we shoot up at queen. Now what is it? The differential well, it's hard to explain really. But I tried it myself, and first of all, you need a really good corpus to have this detailed math things. I could hardly get it working on real-life application. I tried, this is interesting. I tried, for example, I downloaded all the books of George R.R. Martin from the Game of Thrones. So I put it all in there. It did came, things like that work pretty well there. But if I do my text corpus on financial or medical or anything, you will not get that result because it's much more gray. It's never black and white.
So we also did the Bible, for example, and the derivatives of the Bible, various texts, and we were able to find generic text. We could find good word vectors. So our synonyms were phenomenal because they were generic words.
And they were again very black and white. It's
Very
good or
black and
evil. It's
Good
God
evil.
or Satan.
You
It's
could,
not.
yeah, and you could like say Jesus and all his apostles. It came up. And we're like, wow. But you could not go with business terminology. It just becomes much more opaque. Even though you have a great corpus.
So what did we do with Gylo? We trained our word to vector to find synonyms and related words. Often a user types something and yeah, I was thinking about this train of thought, but what are these words? So you can get your related words. Oh, you're talking about interest rates. Think about exchange, or think about exchange rate, or think about monetary policy, central banks, whatnot. And it can do so by these word vectors. It works really well because I've got a big corpus on financial papers. So it gives you word vector specifically, well, trained at finance. If I ask my model to match cancer and AIDS, are these related? Then it gives you no answer because it doesn't know these words. It's going to be a challenge in medicine since you got so many terms. But it is a way to find synonyms, because if you process your text, you need to know synonyms, and you don't always have the synonyms. You don't have a simple lookup table, special medical, because there's so much. So you can look, is the word related or not?
There's a medical dictionary.
A second thing I use is the Google pre-trained word-to-vector model. It's trained on a lot more than I have. It's the whole Wikipedia, the whole of Google News. I don't even know how big that is, but it's huge. And it does very well on generic words. So the combination, if it's a business term, I use my taxonomy to decide on that. If it's a business term I know, then I run it through my own model. If it's a business term I don't, or any term I don't know, I run it through the Google model. Combination works quite well. Other things you can think of, you can exclude stop words. Think about the and a and is and if and then. They don't add much in this perspective to the sentence. They're just that way. So it might work better if you cut them out. On the other hand, you don't need to, because let's say the word the is used so many times in so many contexts, the whole word vector becomes so vague that it's never suggested as the closest synonym, because, well, it's just vague. It's probably only related to other vague terms like the and a are probably related. So don't worry too much about stop words. You can also throw, that's the beauty of it. The number of exposure is also a factor. So if I have some errors or rubbish or whatnot in some of my text, grammatical errors, it kind of get ignored, because if the, let's say, risk management, I find it 1,000 times, but then I got risk management where some letter fell off only a few times, well, it just ignores that, because the 1,000 is so much more statistically than 3. So out goes most of your spelling errors, which is a great thing. And then at the end, you can visualize your word-to-vector model. There are special tools for that. Here's the output of one. If I use the term software, you get this whole cloud. You can scroll around it in 3D. It's really cool. And with all the words, basically, the further you get away from it, the less related they are. But also the color. I guess red is as close as you get. More yellow becomes more unrelated. And the size is the amount of times it might find that word in the document. So bigger circles kind of hold more statistical weight. So they got software here. I see Excel, I see Oracle. Well, these all make sense. I also see extensive. That's a bit weird, but I guess there are sentences that use extensive with software integration. If we look a bit further, we see hardware. That could be an antonym, yet it's still pretty close related. Servers, automated. It's also interesting. You see, if you go this direction, you get kind of hardware. I see hardware, I see tool, I see servers. Well, if I go to another, let's say here, what you got here, environment, analysis, solution tools. So it's kind of, well, everything becomes more or less related, and that's all captured in these word vectors. I said a 100-dimensional word vector, it's just a start. And the bigger these word vectors get, the more detailed these relationships can build, but the more text you need to accurately do so. I use, for example, 300 D word vectors, but the BERT application we talk to use 1000 D word vectors. They become a lot bigger and also a lot harder to process. So you need to find, well, match efficiency with your application. Here's an interesting subject. Well, I think probably not many people can read this, so let me read it for you. It's a little cartoon I found on the internet. So this fellow asked, what does it give you for martini minus gin plus whiskey? Cocktail, the other guy says. Well, see how stupid AI is? Yeah, everybody knows that that's a Manhattan. Yeah, I can't believe it. You trained it on the entire Wikipedia and still it doesn't know how to mix a Manhattan. Yes, I need to train it on a cocktail book. That summons up the exposure problem. It simply gives you what it's exposed to. It doesn't make up anything. It doesn't develop new words or a relationship. It just gets what you feed it. So I guess by doing the whole Wikipedia, it knows what cocktails are. Maybe it knows a few of the names, but it doesn't know enough. It doesn't have enough exposure to the specifics, martini, gin, and whiskey, to come up with the more complex calculations. And that leads us to Gabriella's favorite subject here. Is AI biased? It's the ethics of it. Now, here are two different problems I encountered in my own work. So I had this word vector run on my corpus of 1,500 research articles. They're mainly in finance, in business, but also in business-related papers. I'm thinking political science, sociology, sustainability, and just read annual statements from any company, and it's filled with sustainability, political science, sociology. It's the whole. Everybody is, well, trying to be better in that, or activist. Well, no matter what, it is important in business writing, so that's why I'm starting to include it too. But where finance was really, well, about the numbers and straightforward terms, political science, especially sociology too, well, you suddenly become all kind of new trouble. So let's take this one. Capitalism. These are the terms that found most related, and you can see 59 is the cosine score, where 1 would be perfectly correlated, as in the thing is the same. 0 would be there would be absolutely no relation to the terms. You never get 1 or 0, it's always in between. Here is made capitalism. What do I see? Socialism. Well, that's an antonym, definitely related. Capitalist, that's, I guess, yeah. Communism, okay, also related. Protestant ethic, that's the Protestant word. And industrialism, state socialism, imperialism, industrial society, class consciousness, class struggle. Well, the list goes on and on. Now, it sounds a bit weird. I mean, I want socialism and communism and capitalist. These are good synonyms and antonyms to capitalism. It sounds a bit old-fashioned, first of all, and it sounds very negative on capitalism. So then I realized, oh yes, I added all of Marx's work, the Communist Manifesto, and all 3 tomes of Das Kapital. And now my word-to-vector model has developed a very negative outlook on capitalism. So
instead of free market and all this other stuff, you would think that it'd be like 61%.
So to counter that, to make it a balanced view, I need to get articles that are positive about capitalism. Maybe I need to know, get some libertarian writing in there, some
Ayn
free
Rand.
market advocates. I don't know what exactly, but it's this thing, yeah, you encounter a lot. Is the AI biased? Well, the AI simply does what it's exposed to. It's an algorithm. It's not biased. It's the data set that's biased in this case. Am I biased? Well, I don't think myself as deliberately biased, but I know my big data set is biased because it doesn't give a well-rounded view. And well, second of all, there are over 200 million research articles out there, and I have 1,500, so that's already a personal bias on the selection I made for this.
It's called selection bias.
Okay, now here's another one, even more interesting. I added political science to my taxonomy, where I used word to vector on. Now, I mean sociology in this case, and I didn't scrape the internet for raunchy websites here and there. No, they are all proper academic papers from universities like Harvard and Stanford and whatnot. But be it as it may, if I type in feminism, the first and best match is lesbian. Well, not sure if everybody is happy with that one. Feminist seems a good one. I guess patriarchy is kind of an antonym. Urban sociology, then neo-Marxist. Well, doesn't sound very positive. Neo-Marxist, bisexual, postmodernism, sexism. It's a collection of terms that may be good, maybe not. Others seems a bit problematic. And with this case of capitalism, I could quickly derive, oh yeah, it's all this text of Marx I added up here. I'm not really sure how this happened. I still don't know. Because I'm pretty sure there's no document I added that equates feminism to lesbians. But they're probably used in completely different articles, but with the same context words. You can imagine, well, the words surrounding the word feminism might be the same as these words. So therefore, it's picked up that these two, have very similar word vectors, and therefore it gives me these things as a synonym. So, well, Gabriella, want to add something to it?
Yes, so should I?
Give yourself a quick introduction.
So hi, my name is Gabriella Vispa. I have a background in technology and law and ethics, so I'm very passionate about these kind of topics, especially AI and bias, because I think it's a very big problem. It's getting bigger, and I think it's very good that you're addressing this issue in your own model firstly, because I think that's the first step. And when you're building models or handling data sets, it's the first step is see if your data is can be biased or not. So in this case, you already had your model and your data set ready, and you get these kind of related words, feminism, for example. And I think it's important when we as humans, we have our own human biases. So it's important to be aware of that when you're designing or doing this kind of models, because you can see that the internet is full of bias. Even though it's like from Harvard, MIT, they are articles and people have this bias in them. So it's important to what you're doing right now. So to see what's happening with this kind of words. So using triggering the algorithm. So that by testing the algorithm, you see, okay, if I put feminism in it, I will get this kind of words. And this is not something that happens only here. It happens often in Google. A lot of cases you have. So you have a question for me, I guess. So
No.
Oh, sorry. So for example, this is like a very good example of how like unsupervised models work, because they don't have like there's a correlation or related. Explain this better.
So the question I have for you, because it's understood this happened, how do we deal with this? What do we do? We've had a kind of conversation. How do we deal with, okay, do I, as a user or the developer, what do I do to prevent this? Because I don't know if I can always prevent this issue of bias. So what are some techniques or some ideas that we can just chat about?
Yes. Yeah, I think the first step is acknowledging that there are reinforcement of stereotypical things in your model. So test your model often and see like, hey, maybe this is not going right. And then you have this very challenging next step is to really be creative and by addressing it, you become creative, think about solutions. So what kind of solution you can bring up for this? And you get, for example, devising the data set.
Yeah.
Maybe if you're in a further step, you can devise the model. I've talked about this. Those are kind of steps you can think about. So it's also very nice when you're building things, you can also be very creative because you have a challenge right now. You made something very, very important, very useful for users. Another the challenge lies in how you're going to deal with the biases.
So in this instance, I think that Gilo would probably do is build a lookup table
Yes.
for all of these kind of issues. Like if we have feminism, we set up our lookup table for those keywords that we think are kind of good synonyms, antonyms. I think that's a first step. We have a biased, what we call tone and bias tool. So the bias tool will then only after the fact find these issues and say flag them, but it's contextual in the sentence. So I think that the lookup table is probably the best thing because there's no way I can build another algorithm that actually deals with this issue because it's just more work. So I think that's what you have to do in like just making it, keep it simple, stupid, like lookup table is gonna solve it. So let's make, take all of my objectivity, I have a database that I use with BERT. So I can look at anything that says, for example, retarded. I have words for not saying retarded. So I can take those words and put it in my synonym tool, not only in my bias tool, and I can have my synonym list and then always have our app provide those synonyms rather than have it. So I can kind of like intertwine two different models and help each other kind of solve the problem.
Because they did some in a case they did like verifying the model, so they went to like add more because you had a lot of nurses. They made a relationship with nurse and women. So by verifying the model, they could make they enter more male nurses. So the algorithm thought, oh, okay, so you also have male nurses, and then you get other outputs. So I think the verifying is very good too, especially when you're already in the algorithm, you already have one. But for you, and if you one day going to make an algorithm model, please address these issues beforehand and think about ethical and ethical consideration before you yes.
Why does it matter if data sets are biased?
Why does it matter? Because you keep like these values, societies. Because when these are biased, we keep thinking like, oh, feminisms are lesbians, and that's not true. So you keep these values in society, and it can be very dangerous. It can be very discrimination. Yes.
It can be offensive.
Also.
No, but the data set itself is harmless. It's just data that is collected. It's only dangerous when a choice is made based on that data.
Yes.
So why does it matter if the data itself?
Because when it's going to make those choices, you have to start with the model, with the data set, right? So your question was, it's not the data set is wrong, or?
No, but like for example, if
Yes.
you're working with synonyms and antonyms, these are going to be synonyms and antonyms and so forth. So why does it matter if it's biased?
Because the person will use it and it's our tool in the Gilo app, for example, is a tool for people to write academic and business documents that are, we believe, are kind of grammatically correct, are academically correct based on certain rules of punctuation and all those other things, and biased is unbiased and logical. So for us as a company, we value these things. So this is why it's important for us. Maybe in other instances, it's not important.
I think it's always important for me especially. I think it's also important because technology is not neutral and you have to be aware of the power it has. And this has power. For example, in writing academics and stuff like that, if you have these kind of biased data sets, it can have an effect on society. Maybe you don't see it directly, but it will have, because you keep these kind of words as or relationship, these words as something that's facts, and that's true. It's not true. You're not a feminist and lesbian, for example, or you're not. Do you get what I mean? Or
No, but
yeah.
Right now it doesn't say that feminism is equal to
No,
lesbian.
no,
It's
I
just
know.
related.
And I'm just giving you like
Yeah,
an
exactly.
great example because then you can know. Sorry.
No, I understand, but like ethically, if you were to filter out bias, then you in itself are biased.
Yeah.
So.
That is true, because then that becomes the researcher's error. It's what we call the research bias or the another word for it. It's another bias. So unfortunately, you have to look at all these kind of filtering. When you're building an app, you have to know the response bias. You also need to know the research bias. You need to know the AI bias. So all these things as our company, because that's my background is research, we look at all these steps. But in this instance, I think it's important for Gylo because we live by our word.
And you can also imagine, well, it's more like a practical thing. If I want to have this app for academia and I come up with these results, I'm probably going to get banned. You know,
But
it's
then your
already
data sets
biased.
Excuse me?
Yeah,
And then your data sets would be wrong.
explain that to, well,
No, but
academia.
in reality, your data sets would be wrong, correct?
Yeah,
Yeah,
the data
yeah.
set is biased, you can often conclude. For another thing, well, I don't have religion as a topic, but I can imagine if I would add that, you gotta be really careful there. It might lead you in a lot of trouble if you come up with, well, with bad examples.
Yeah, I think those are very great examples, and I think I'm just making now like this example for you, but it's more to see like the bigger picture of it because it has some consequences, and it can be indirectly, implicit. It can be so many ways. It can have a negative impact on society. That's something you have to be aware of. And as a company, if you have those ethical values, it's very good because then you keep building models that are ethical, and that's eventually the goal. I hope,
Yeah.
I guess.
So we went for our bias tool, we have partisan bias, we detect for it. So what I've done is I've made sure I look at everything from, let's say, left, right, and moderate. So I detect everything that if it says something like leftist, I take that out. So we are making sure that people do not, we kind of recommend don't put leftist. We don't say, Republican is not the same as a conservative. So like these kinds of words, but maybe other companies won't care, but we as a tool care because we are training people to recommend this in their work.
And you got, of course, terms that change in meaning throughout the time. For example, one of the terms I encountered in this model is homosexual, which, well, it's not really used anymore today, or it can maybe a certain race-related terms that may be common like 50 years ago now are seen as really offensive.
Yeah, we had like two spirits, fine is two spirit, but Erwin looked up, for example, what was it?
It's equated Eskimos to homosexuals, which is, I guess, problematic at multiple levels because both Eskimo and homosexual are already a loaded term, and then when you equate it to, well,
and then we
Probably
looked
some
at our
tweaking about
our data set and we looked at, it was two spirits, and two spirit is word for Native Americans. And then there was obviously an article that we had dumped into the system that was, or a definition, and then it kind of found the relationship. So we're definitely gonna go in and, based on my bias tool, make the lookup tables for the synonyms, because that's the only way to remedy this issue.
yeah, for now, but there should be a more structural approach to this somehow.
Definitely. Well, thank you so much.
Thank you,
For your
Gabrielle.
questions. Yes.
Okay, well, that concludes our discussion on word vector. Now let's go on to deep learning. I hope I can keep it a bit, well, not too complex since most of you are not IT or data science students. Anyway, the first thing, well, I assume you know some basics of deep learning. You create a model, and the model looks a bit like the human brain, as it has neurons on it. It has pathways between the neurons. Signals travel over these pathways, and somehow it's interesting because both with our human brain as with our neural network, we can't pinpoint exactly how ideas or thoughts or conclusions are formed, yet they are mysteriously through these neurons and these signals that travel in between them. Anyway, why is it suddenly everywhere? Because AI has been around since the 70s. Somebody already thought we should use the human brain. Well, they obviously lack the computer power, the data, and then such the methods to do so, well, in a proper way. It came back in the 90s when computer power became more of a thing, and especially the internet revolution gave access to data so much easier. But it was still lacking, and now it's, well, a third wave, you could say. You have AI winters and summers. We've been in a winter since the end of the 90s up till a few years ago. But now it's suddenly everywhere. It's in the news. Everybody's talking about it. All corporates want to use it. Academia is researching it everywhere. How come? I found three things that changed the last few years. First of all, the Python libraries we talked about, and specifically TensorFlow and PyTorch. They too make it that I at home with my desktop computer can start developing an AI model. Before that, they're introduced, I believe 2015 or something. Before that, I need to have a PhD in computer science and mathematics. I need to go to the data center of Google. I need to do a lot of programming. I mean, it was really hard. It was definitely not for everyone. You needed a team of people to do this. The second one is easy access to big data. If you look at the internet, well, of course, data is everywhere, but also the way you access this. There are certain websites you can just download whole data sets. You can start playing around with it. You have, for example, the MIST data set, I believe it's called. It's like they have 10,000 little pictures of handwritten numbers. So you can easily create an AI that recognizes handwriting and say, this is a 6, this is a 3. And sometimes, it's like really squiggly. So it's hard to detect for a human, but AI is better at it than me. I tried all the examples. Wow, it detected that. I would say it's a 6. Well, data can be found anywhere if you look, but if you want to have your specifics, which a company or like Guido also, you have to develop your own data set still, and that's a lot of work. Be it as it may, you can access big data, you can find data on about anything, and you can get started on that. For example, I created my whole text corpus, which I ran these things on, but well, I didn't write that text myself, neither did I have copies. No, I just go to Google Scholar or other website, I get some of the research articles, and I have a big text corpus. The third of all is the GPU. A GPU is a graphical processor unit. It's basically a video card. It's a funny story. These things are really developed for video games. Everybody loves them, play video games, especially the rendered one, the 3D shooters. It uses a lot of computational power to create all the 3D world this video game takes place in. That's what you do with the video cards. How is it different? My processor, I have a pretty good desktop PC at home. It has 12 cores in the processor, so it can handle 12 processes simultaneously. My video card, on the other hand, has 512 cores. It can handle 512 things simultaneously. It does so a bit slower. The core here is not the same, but let's say it's half of the power, and you still can handle so much more simultaneous. And we'll see in a moment, these neural network, it's all about parallel processing. Every of the neurons, and there could be thousands or millions in the network, needs one process. Of course, you don't have a million cores available, but if you schedule them in 512 cores instead of 12, that's making a massive difference. And with the help of video cards, you can accelerate your AI deep learning with a factor 10, 20, or 100. I did so factor 20, I believe, on a simple desktop. I think, okay, that's just Guido. They have a desktop with a nice video card, but big corporates use the same. Google, well, they developed their own GPUs specifically to handle these problems, but they're very similar to graphic cards. NVIDIA, I believe, has a record in how to train certain models, including birds, how fast they did it. They use their own cards, their own video cards, just a professional version of it. And as soon as NVIDIA says professional, it means the price is 10 times higher, the performance is a bit higher. So most people are best off, well, with this one specifically, the RTX 3090 is kind of the holy grail of deep learning. It costs about 2,500 euros, it's not that cheap. But it has a lot of memory, so your model can be bigger, and it has the fastest cores until the next generation comes out. You kind of can't get better than this for consumer tech. Then you go to the pro line, and they're expensive.
AMD has equals.
I know that's a good point, but NVIDIA is integrated with TensorFlow and PyTorch. AMD is not. So they have this specific thing, it's only on NVIDIA cards, they have tensor cores. And these are the actual work, well, you already see it in the name TensorFlow. A tensor is basically a matrix of numbers where you do linear algebra with. And that's tremendous, how to say it, speeded up the game. For example, I had a BERT model where I classify sentences. What field are they in from one of the 20 fields of business? It's 60,000 sentences. I run it on BERT, on my desktop computer, on my processor. It took, well, I usually started it in the evening. I went to bed and I was hoping for the best when I woke up that it's done. Often it was not. At the end, it took like 15 hours. I moved it to my graphic cards. It took 45 minutes. Now, it becomes practical again. If things run for 24 hours or more, it's not practical anymore because you wait 24 hours, you discover there's a little error in it. Oh, I didn't do that parameter right. Or, oh, my data set, it missed something. Oh, I got to train it again. Well, you can wait another 24 hours.
Sounds like the ASL over again.
Yeah, exactly. Therefore, these cards, they're a must if you're in the
Yeah,
field.
there's a must. We had built our clarity model based on this, and our clarity model has like multiple BERT models as well as spacey models, and had done one for confusing language. So there was something that, for example, something Grammarly doesn't do. We were able to like look at words that are confusing, and Erwin and I were like, okay, how are we going to train this model? It's got thousands of examples, and we need to do it like within 30 minutes. And he had to do this switch because I had to test it while he was at work. And I couldn't wait for him at the night because I needed to push to my next model I had to build. So this is very important, this factoid, that it just changed. So I was then able to, on my own when he was, because I don't use BERT. I use BERT, but I don't run on my machine, what runs on his machine. And it was quick, and I could tweak my models immediately. But
And if you have a
otherwise,
big power supply, you can stack these cards. You can put 4 of these cards in your computer, and the parallel processors are used in parallel. They scale up real well. While with processors, it's hard to use more than one. Anyway, it's not really about that. We want to talk about NLP. First, let's take a quick look at a deep learning model so we understand the basics at least. A deep learning model would look a bit like this. We got our neurons, these are the circles, and there's an activation code in there. It basically takes all the information from the previous layer, it calculates something, it adds up the signals, and then it decides it fires a signal or not. And well, a number, basically a floating number, 0.9154, whatever it calculates. On these connections, you put weights, like there's a 1 or there's a 0 or a value in between, so you can suppress certain neurons or make them more important. The first layer is the input layer. You get your data in there. The last layer is the output layer. You get your predictions in there. Now it's an interesting thing because you have control over what comes in the input layer. Let's say I do a sentence analysis. They say the service was terrible. I had to wait 20 minutes. First you tokenize it. The service was, etc. Then you vectorize it. It's the vocabulary. The is the third word in my vocabulary, etc. You could vectorize, word vectorize it after that. We'll get into that later, but this is a simple example. So you basically put these numbers in. This becomes all kind of one thing. It's not that the information, that this information itself travels through the network. It simply triggers these signals from the neurons to go to the next layer. They pick up signals and they trigger their own signals until eventually it comes to the output. And let's say the output here, signals with a much higher weight come in, and it concludes 0.97% probability that it's a negative what do you call it, a sentiment, as in a sentiment analysis. Well, the service was terrible, that does sound like negative. 2% that it's a neutral phrase, and well, almost 0% that it's a positive phrase. And well, it's kind of the magic of deep learning, because these orange neurons, they're called the hidden layers, and they're called hidden for a reason. We have basically no idea what they're doing. We have no idea how they pick up patterns. It's we know what goes in and we can read what comes out, but what happens here is a black box. But it's really good at picking up patterns in these numbers. It's always numbers, it's always a matrix of numbers that goes in. It picks up patterns that you maybe have missed, that you would never see. It's very good at that, and it comes out with predictions like a class or a number. Like if I have a data set with housing prices, and including that is the amount of rooms, and if it has a garden or not, and if the neighborhood is nice or not, then it can predict based on that what your house is worth without really knowing the house or all the details about it. Well, here you see quickly how does an activation function work. It carries all the weights from the previous connection. It's basically the signal the previous neuron sends plus the weight that's on that connection. It adds them all together, like in this case, it adds all the input layers. Then it decides whether it activates or not, and then if it does, it sends one signal or many signals to all the layers, to all the neurons in the next layer. When it comes to the outputs, it says, for example, negative 0.97%, but what if on my trained data set, I here have labels, I say the service was terrible, it's labeled positive. Well, the service was great, maybe. But here it says 97% sure it's negative. Now, that's not correct. It has to go back. It's going to change the weights here. And therefore, it will detect different patterns. Or therefore, think a bit like, almost like, the pinball machine. At the top, it goes through all kind of weird, it bounces around almost, and you don't really know what path the ball's going to take. It's going to end up at the bottom. How it gets there, we're not really sure. Be it as it may, it changes all the weights, and it comes up with a new probability until it's happy with the probability outcome, that's the predicted label of the sentence matches the label that I actually put on it, the real label. At that moment, if we're happy with the training, we'll save the model, we'll freeze the model, which basically means we save all the values, all the weights that are put on all these connections. That's our model. Then we use the saved model, we can put new sentences in it. The weights stay the same, but it should predict, therefore it should generalize whatever, we want to predict. And so there's a lot more to it, but I guess that's not really the aim of this course.
So we can do an example here. Can we do an example with that? So if we look at the confusing, it's an element of our clarity model we built. Let's say if we want to look at a sentence, and a sentence has the difference between the words differing and conflicting, okay? And those are, they sound like synonyms, right? But they're not. So you have to look at the context of the sentence. So you can run a BERT model, you build a bunch of sentences in the black box, you choose the sentences that have the words differing, and that's the supervisor, you tell it, okay, differing in this context, correct? And then you change the word to conflicting, you can change those as your incorrect sentences, and then you can build your model, and you can then give an example of when it should be differing, okay? And not conflicting or vice versa. You run it through the system, and then you can actually then predict the outcome and the recommended, whether it's incorrect or correct usage. And then you can find out whether you should change the sentence, that word in that sentence to the right one. So this is it's very practical from a word level. And you can do it from a phrase level, and you can do a sentence level, you can do a paragraph level, document level.
It's all depending on the inputs, what you gotta put in there, what comes out of there. But the beauty of this thing, since we don't really know what happens in the hidden layers, it's also, you kind of give up control. It's hard, if you get this output, you can judge if it's correct or not, but you don't know how it got there. And I guess that's one of the points Gabriella tries to make with ethics. If you, let's say I'm running a bank, and my AI algorithm decides whether you get a mortgage or not, and I look at what area do you live in, oh, that's a bad area, so I'm not going to give you a mortgage. You say, well, that's racism or something, or at least explain why you don't get this mortgage. Well, the AI predicts that you're not going to pay it back or something. Yeah, why? We don't know. It's hidden layers. They picked up a pattern of some sort. I mean, yeah, that's not going to fly. You need to explain yourself to make certain decisions.
That is the problem with AI versus like statistics. If you look at statistics, or mathematical probabilities. You can test for the p-value, and you can look at other kinds of ways. I mean, if, depending on whether you're doing the regression, simple regression, or structural equation modeling, or meta-analysis, that allows you to really look at different kinds of like the root mean square. So you really know whether that model is correct or not. So you can test for that. But with AI, guess what? You can't.
Well, there's a
There's
solution to that,
accuracy.
complex. What you
Explain.
simply do, you take your data set and your prediction and you run it through an old-fashioned statistical program like SPSS, and you get your R square and everything. It's a lot of
A
work.
lot
It's
of work.
definitely something where work needs to be done, but I have no idea how that is going to be done, or it's even possible, because it's also the strong point that it's not in your control. It will find patterns you never thought about. If you want control, then you lose the flexibility and the creativity of the thing.
So it's more like exploratory versus confirmatory research. You know, you can explore with that and just put whatever in the system. But a lot of other models are confirmatory. You kind of know what to predict. So it's also, you have to have a statistical mathematical mind when you actually build these models. You can't just nilly-willy do it because, you know, it's a black box, but you have to think about the black box, what can go in it.
I guess that's the main control you have, is your data set. That's where you can apply the control. You, can steer it. What do I expose it to? And how do I label it? Anyway, let's start with a simple one, categorizing text. Now, why do we want to categorize text? Text is text, it's not always the case. For example, here I have a financial text. And the term is stock. Well, we all know stock, the New York Stock Exchange. I bought 100 stock of Apple. It's a share of a company. That's true in finance, but if I go to economics or accounting, stock may mean an inventory item, like the iPhone store has 100 iPhones on stock. So if I give recommendation, what does stock mean, and I don't know the context of the text, I can give the wrong recommendation. It becomes even odder when you talk about acronyms. We all know acronyms, and usually the same acronym means something different in a different field. For example, IP. Well, in ICT, it's the Internet Protocol. What's your IP address? We all know that one. But in business administration, it would mean intellectual property. What's your IP? Your portfolio of brand names and such. Many acronyms you can think of mean something different in a different field. So when you want to analyze your text, you want to do acronym resolution. IP needs to be the same as intellectual property or Internet Protocol, but you don't want to treat it as different words because they're really not. So first we need to classify the text, and if it's business administration or economics, IP would mean intellectual property. If it's the other fields, it's Internet Protocol. Otherwise you end up something like this. Internet Protocol can be registered in any one of the following three methods: copyright, trademark, or patent. Sounds off. In the United Kingdom, a product life cycle is a publicly held corporation. So, value-added reseller has become the standard measure of market risk employed by financial institutions. No, that's all wrong, because the field is not classified. But you can imagine a student who's not that familiar with most of these terms. They might, oh yeah, there's, he puts it in and he moves on.
I had that with NLP.
Ah,
Because I know NLP is.
Neurolinguistics.
oh
Oh
yeah.
my God.
I used that to quit smoking some years ago. It's a good
Yeah, the
technique.
book.
The neural-linguistic programming.
Yeah.
Kind of a pseudo-psychological way to reinforce your mind to, do certain things like quit smoking. Anyway, back to our document classifier. So we know why we're going to do it. So what did I do there? Well, I downloaded 1,500 research articles from Google Scholar. Well, it's a link to Harvard or MIT who writes these things. And I got the full text, not just the abstract, and I labeled them. This is in finance, this is business administration, this is economy. So we load that all in our database. Then we have to split the corpus of text in a training set and a test set. Because as I explained in the neural model, the values, they change, it goes through, at the end you end up with a prediction. Then it's probably not right the first time, so it's going to go back. It's called an epoch. You can train it for 5 epochs, it goes back 5 times. You can do 100 epochs, depending on your model. But you want to see at what point do we have success. So we take 90% of this document is used as an input for the deep learning model to train it, to get to know the patterns. We use 10% for the validation. So basically at the end of an epoch, it freezes the model temporarily, all the weights keep the same, and it runs the validation set through it. Then we can look at our accuracy. We got, what is this, 150 predictions on 150 documents. Let's see how many of these predicted labels are the same as the actual labels. In the first epoch, in the first training round, it's usually very poor, maybe 30%. In the second, it's 40. The fourth, it's 50. It goes better and better. I ended up on this model at about 90%. It's a good outcome, by the way.
Yeah.
Saying, oh yeah, so that's why we need to split it, basically to validate whether we're on the right path with our training. At the end, most people forget about this. When you think your model is in good shape and you know how many epochs to train it for, you put all the validation back in the training set, so it has more sentences to train on, so it becomes a bit more accurate. But you're kind of going blind, you're driving blind without a validation set. You really got to know your model is solid, otherwise you have no idea if it's good or bad.
Could you explain why, like, some of our models required like 5 epochs and it didn't change? Like it went from 75 to 80 and then it just stopped? And then at 5th epoch, and then with yours, why 150 for this
Well, it's a
document
good question.
classifier?
It all is depending on your input sets. And here, for example, you get the text document of a research article, which is on average 20 pages of text. So you got so many words to work with. It's actually pretty easy. Just try reading a document, and if you read all 20 pages, you will know what field it's about. The AI will pick it up too. But if you have one sentence, there's a lot less words. So you kind of got to squeeze every last bit of information out of the few words you have. If you would have one word, it might be impossible to classify. Classify IP, no further context given. Yeah, it could be multiple things. So that's why I'm doing the document classifier first. It has an abundance of information and it's really easy for the AI to find the patterns. In this case, how do we do it? So in goes the text. We make a vocabulary, a vocab, which is basically, we have an algorithm that goes through every word. Is that in the vocabulary? No, we put it there. Study, put it there. Weather. At one case, the is found a second time, so it's already there. We just mark it 2 instead of 1. It simply counts every word and the frequency of the words. Then we know the frequency, we know all the words in there, and we know the frequency. So we get a matrix here. You got to see this, every line is a document. And there are, in this case, 25,000 values, not just 6, but 25,000 didn't fit on my sheet. And it's basically a glorified word counter. You see, the first word is the number 1 in the vocabulary is de. So the first value, 492 instances of de in the first document, 458 in the second, 531, etc. The second word is of, 304 times, 280 times, etc. Well, you can imagine this is not going to mean much to an AI. De is in every word. There's no what they call discriminatory effect. You cannot say this is that is that on the word de. If you go all the other side of the vocabulary, around 25,000 words, the least common words in the text documents, non-stochastically or Alice Patrick or international, well, it's a mixed bag. I know stochastics, but non-stochastically, it's a very weird variation. Alice Patrick, I suspect, is a name, and international simply had a few characters missing. So you come up with oddballs and something that also has very little predictive power. As they say in finance, the best fish is between the head and the tail. You can chuck away the head and the tail, you want the middle part. That's also here where the knowledge. You encounter words like model or market or stock price or If you have other fields, maybe feminism or Marxist or, well, medical terms, anything, they're usually in the middle. They're sometimes used, but not all the time. These are the words, well, that the AI is going to use mainly to predict. Via this May, our glorified word counter now has 25,000 rows and 25,000 columns representing the 25,000 words and 1,500 rows representing the 1,500 documents. And why do we do it this way? It's a linear algebra. It's basically, if you have a matrix of numbers, you can do a calculation where you simply do an addition, a dot product of the matrix, and you have the whole matrix, this whole thing in one time transforms to, well, whatever it's transformed to. Well, with normal math, you would have gone through all the numbers. Okay, start here, iterate through all the numbers, multiplying by 2. It's not efficient. If you put it in a matrix format, it's also sometimes called a tensor, hence the name TensorFlow and Tensor Cores. It specifically does matrix calculations. That's what it makes, well, I already explained it can take 12 hours to train a process, and I've got a pretty good desktop PC, so you can imagine the amount of calculation that goes in this thing. It's off the charts. It's, I guess, a reason why AI didn't work 20 years ago, because the processing power simply wasn't there to do it properly. Anyway, here's our simple model. It probably has a few more hidden layers to pick up these patterns, but this is our input now. A lot of people make the mistake, if you talk about NLP, that they think words actually go into it. No, it's this. It's the human eye would simply not understand what it is. It's just a big matrix of numbers. It finds patterns in these matrices through these hidden layers, and out comes a prediction. So in this case, my document is pharma and French size and book to market factors and earnings and returns. I think they want to predict the stock market prices there. 97% probability that it's finance, which is correct. And how does this work? Well, sort of from a, in this case, it's TensorFlow perspective. I downloaded the model from the Google website. It gives you all the layers and all the specifics. I guess I don't want to go in details in this course. Then it goes through 30 apples, 30 training rounds. And what I mainly look at, you have the loss function and you have the validation accuracy. The validation accuracy is the prime way to see if I'm doing it right. It's basically the validation set, which was kept separate for validation purposes. Again, it determines, is the predicted label the same as the actual label? If yes, well, 58% is accurate the first epoch. Then we go to 78. Oh, that's a big change in one. Usually it changes a lot in the first few, and then it starts to top down, sometimes about 5, sometimes 10 or 20. So here, 30 epochs later, we are at 0.889, almost 90%. That's a good accuracy. There might be improvements, but in general, if I would have a sentence classifier, that would be amazing. But the document classifier, it has so much words to work with that 88 may be a bit on the low side. It depends on your exact application.
But I wouldn't say that's garbage.
No, it's pretty good. And if it makes a mistake, it's often a little mistake, as in your finance paper is ranked as an economic paper, but not as, let's say, medical paper or data science paper. So now we got this model, we save it because we're happy the way it works. And now let's try a new prediction. So you can only use new files to make new prediction, because if you use your files that the AI is exposed to in its training, it will guarantee know the exact answer, because it already, oh, this document is that pattern and that's that label. So if you would run your data you used in the training for this validation, it's cheating. You always get 100% accuracy. So I get a new file, my thesis, for example. Process is the same as how you train it. You get your text, you vectorize it with your vocabulary. Then you run it through the saved model. Out comes a prediction. It looks a bit like this. That needs some processing. What do we got there? We got numbers that almost infinitely small, 1.8 to the power of e minus 25. Well, I'm not sure what that is. That's a 0.0 with a lot of zeros and then an 1/8. They all look like that. Oh, but here, 1.00000, that's probably my fields. A probability distribution, if you're new to statistics, it's basically, we want all values are between 0 and 1, where 1 is highly accurate or highly probable, and 0 is not probable at all, so basically wrong. And they must add up to 1. So if we see that one number is almost 1 by itself, well, we got a very high accuracy on this is our field. So I need to fetch our saved labels because, well, all it does, it say the sixth or what the fifth, 0, 1, 2, 3, 4, fifth output is the 1. I see in my label file, that's finance. So my predicted label is finance, my real label is finance. So that's a good prediction. And again, why did we do it? As soon as we classify what the student is writing about, we can give him targeted advice, as in we know exactly what a definition of a keyword is in that field, not in the other field. Or for example, one that I put a lot of effort in is the citation advisor. Everybody's probably familiar with Google Scholar. You type the keywords in there, you get a lot of results. Well, I unfortunately only have 1,500 papers, not 2 million. They're kind of handpicked by me and Maha, but we do know the field of business. So it's the most important thesis, the highest citation scores, the seminal works and such. But since we know the context of the user's writing, we can specifically rank them based on keywords. First, if I look for risk management, I get financial papers based on risk management in the financial words, financial risk management. I have a portfolio stock. How do I lose as little money as possible in the stock crash? That kind of papers. But risk management, it's a very broad term. Business administration does risk management, well, how your company should stay afloat during a natural disaster or something. Or I guess medical risk management, they probably have very different applications. But I, as a finance, I'm writing about finance. I don't need to know about medical risk management. But with Google Scholar, it doesn't know your context because you just type keywords in there. So it gives you a whole bag of articles. Most of them are useless. But based on the classification of the document, I give targeted advice. These are the acronyms. These what your acronyms mean in this field. This is the proper definition. These are research articles.
What is your theory? Why do you think Google Scholar versus like Gilo, we're building, differs? Is it because they're database driven, or I mean,
No,
they do have.
It's a website. It's not an application. They don't know your whole text.
Oh yeah.
You just type risk management in there, and that's exactly what it does. It finds you the documents that. Well, are about risk management. The more risk management is mentioned.
So they're not customizing based on your text. Does that make sense?
Okay, now we're going to talk about BERT. Well, BERT is one of the state-of-the-art models. It's been introduced in 2019, and it completely revolutionized how AI works with sentences. The accuracy of its predictions are just in another league from everything that came before. So I would say forget about recurring neural network or LSTM, the long short-term memory. They're obsolete in my opinion. We'll use BERT. And why do we use BERT? Well, BERT's got its limitations first of all. It works on sentences. And you can actually put multiple sentences in there, but no more than 512 words, which is a small page of text. And it becomes exponentially more difficult to train. So I cut off my sentences at 64 words, and it's still manageable. It's already a long sentence anyway. Anyway, what did we do with BERT? BERT is the bidirectional encoder representations from transformers, okay? Well, we like childish names, I guess, in the field. It's always Bert and Ernie and Elmo, Transformers, whatnot. A lot of the AI models work like things I explained before. Like I need to build a corpus of text or a data set, and then I can do something and out comes prediction. With BERT, you can use a pre-trained model. So nice people at Google, they developed this BERT model. They trained it on a large corpus of text, I guess Google News and whatnot. I believe the Gutenberg Book Initiative, which got, well, about any book that's not copyrighted in there. And it's got a great knowledge of generic English terms. Therefore, they save the model, and then you can slap at the, the image of the neural network at the end here where the output layer is. You just add your own little layer on top of that, and that gets your own data in there, gets your own, well, whatever you want to come out of there. So you have your pre-trained words, and then you have your fine-tuning. And we can use all the knowledge of English that Google trained in this generic training, and we add our own domain-specific knowledge. That's one of the steps that simply makes it much better. Another one is the transformer aspect. What is a transformer? In this case, it's an attention mechanism. It sees the words coming in, and it kind of knows which words are important and which words are not. It can put values on there, and therefore it doesn't waste processing power on every word, but only on the words that it thinks matters for the prediction. How does it do that? That's a hard question. I'm not going to answer that now. Okay, what else do we got here? Yeah, BERT is bidirectional, as in it tackles a sentence from left to right, but also from right to left. Why is that important? It can find context of the words after the word itself. Think, if I read, I go, BERT is a stacked transformer, but I don't know what comes after it. I already have to judge every word I read when I read it without knowing the proper context. But BERT, it reads from here, or basically it just takes in all words simultaneously, and therefore if I say I went to the bank, what is bank? There's text behind that. What is bank? Yeah, first thing I come to mind is I went to a financial institution to check on my savings account. I went to the bank to do something. But it also can say I went fishing. I went to the river bank and I threw a rod and I caught 3 fish. I don't know at the point I went to the bank what bank is, but I'm sure the context is explained. I went to the bank. The river was overflowing, so I couldn't fish. Oh, the bank is the river bank. BERT, since it knows also what's after the text, can use that information in the transformers in the way it applies those weights to the words. While previous algorithms simply go from left to right like a human and can miss important context. And then another one is, well, that is not new, but it's important. Every word in the sentence is captured in a 768-dimensional vector, or bigger versions of BERT do more. Why is that important? As I explained in my document classifier, we've got so much words to work with. It's not important what the weight and all. We got almost too much information, easy peasy. But in a sentence, we'll tackle a few sentences. They're often vague, like what is it? So you really need every bit of information. And when it may not be that familiar with a word or can't find a pattern, you have this word vector, so you may be able to look at very similar words and just make a decision based on that. Well, if it's just a word represented by the number 12, then that's what that is. The number 13 is not related in your vocabulary.
Do you want to give it, are you going to give examples?
Yeah, we'll get there. I guess this is kind of the same. Yeah, so it's a pre-trained model. We fine-tune it. It took Google 4 days on their massive servers to pre-train this model. So it's got so much English information baked in there. The record holder now, it became a challenge, the BERT challenge. Can you train the BERT model? Well, even on this fancy 3090 graphic cards, I wouldn't try it at home. You need like a stack of those things. NVIDIA has a stack of those things, so they did it in 43 minutes. I believe they encountered hundreds of their professional video cards for that. Still, if I do the fine-tuning of BERT, it's a slow model because it vectorizes my sentence. There's so much data coming in, and it needs to be processed in such way. I wouldn't try it without a graphic cards. That's a fun thing. I kind of missed that earlier when I said use a graphic cards to train this thing. Well, most students have a laptop. Graphic cards is not that great. You have this thing, Google Colab. And Colab, you can use the Google video cards, the Google servers for free. Of course, there's a cave out when they're not used by paying customers, so usually at off hours. But I had some students from Tanya who worked with the Bird model. They did everything on a simple Apple laptop using Colab, and it worked really well. So if you ever want to get into these things and you don't have the proper equipment, look at Colab.
Colab.
Okay, so here we have an example of my sentence classifier. In goes a training set like this. It has sentences and labels. This is in the field of law, of business administration, of human resources, accounting, finance, etc. Most of the sentences are pretty self-explanatory what field they are. If you say, we cannot assure you these investments will be successful. That's clearly finance. Or using marketing research to find and evaluate new opportunities. Okay, that's marketing. But what if you get a sentence as the drought in Russia that year added to the problems? Geography, it's not even a category. Economics, maybe you talk about the farming industry in general of a country, or maybe the Soviet Union had this problem. Maybe it's political science that it led to the down. I'm not sure. So not every sentence is clear if you just judge it by the sentence. Anyway, we take I managed to gather 60,000 sentences and label them with what field they're in. Well, I must say most of this data set I didn't type myself. I got my database with research articles again. I had to clean up some of the text, but then it's simply, this abstract, for example, is about business administration. I'm going to label every sentence as business administration, which on average is correct, but even in business administration, there will be a field like, we used regression analysis to come up with a conclusion within the confidence range of 95%. Well, that's statistics, that's not business administration. But I'm hoping with this approach that I've got so much sentences that these errors kind of, cancel each other out, and that the broad term, will remain.
What is your percentage? Would you get from
I'm about 75%. I don't think you're going to go any higher without really labeling everything yourself, which I'm not going to do.
Yes, too much effort.
And again, we randomize the data set as in the rows. So ICT, accounting, it's not, the label sticks with the sentence, of course, but otherwise you get a file. The first 1,000 rows are finance, the second 1,000 are business administration. If I split it for my training and validation set, then maybe validation is all in the same field because I didn't randomize it and that wouldn't work. So we need to mix it up and then split it in training and validation. Then it's going to look a bit like this, the output. So the sentence, the commonly used financial ratios fall into 3 categories. Well, our label is finance. We tokenize it, so Bird tokenizes it, so we get all the separate little words. Then it uses a vocabulary of about 30,000 words. You get a matrix with numbers, like apparently is the 1996 entry in the vocabulary. And based on these numbers, it generates a word factor of 768 dimensions, which is quite a lot. It tries to really squeeze the most information as you can from the words in the sentence.
So don't forget, BERT is a glorified classifier. And it's like, if you've ever used statistics, they have classification tools before. And it's kind of like a higher end version of that. Classification in market research, for example, was not used often. I mean, yeah, you could use it, but people didn't use it. They used more kind of like fancy stuff like regression models, SEM, structural equation modeling. But it's amazing how now, because of the AI, it just uses something that was like not used much. It can actually now really classify text, and that's just what it is, a glorified classifier, a filing cabinet, but it could do really cool stuff. We can talk about
There's a lot more, but I guess there's only so much time you can talk. Anyway, let's try an example and see where the complexity comes in. So we got the sentence, No matter how the Evergrande drama plays out, Evergrande is the biggest property developer in the world in China that lately sort of went bankrupt. No matter how that plays out, whenever it accumulates with an uncontrolled chaotic default and or distressed asset sale liquidation, a controlled restructuring where bondholders get some compensation, or with Beijing blinking and bailing out the core pillar of Chinese housing market. If you just count the keywords, I would definitely go with finance. Liquidation, sale, distressed assets, chaotic default. There's so much bondholders, so much finance in there. I think I would have labeled this a finance
I'd
sentence,
say real
possibly
estate.
economics. Well, what do? We tokenize it, we run it through the vocabulary, we get our word factors, then we used our safe BERT model, including the pre-trained BERT and the fine-tuned BERT, so it knows generic English and it knows my business sentences. Out comes the prediction, which is a bunch of numbers again. We pick argmax finds the maximum of the arguments, well, which is basically search for the highest number. That's number 15, fetch our label, real estate, what do you know? And this is really something you could not do before BERT because it is so vague, this sentence. It would be not chosen as real estate, but apparently it knows about, well, housing market is a clear indicator. It probably doesn't know Evergrande. It's a recently developed company name, but maybe it does, I don't know. It's probably in Google News mentioned.
Erwin, how many sentences do you think that you need to be able to do this classification well, to get at least a 75%?
That's a good question. That completely depends on the problem you're tackling. If I have a really simple problem, let's say, BERT, I want sentences to be labeled, it contains the word financial in it or not. Then within a few dozen sentences is enough because there's financial in it or there's not. So it's really easy to find the pattern contains financial or not. I'll do a bit later the chatbots we're looking at. It has a quite easy problem as the user intent. There are 5 user intents. I'm looking for quotes, I'm looking for a research paper, I'm looking for definition, etc. So I wrote sentences for all, what can the user do? Give me a quote on Elon Musk, or Elon Musk quotes, or George Washington quoted. They're all going to be quotes, or define risk management, or what is risk management. These are all. But the problem is very limited. So with 1,000 sentences, I had a great result, almost 100% were excellent. Because the problem is small and confined, you don't need much sentences. Here, the sentence classifier, just by looking at how many business terms there are, well, 60,000 may not be necessary that much, but 10 of 1,000 would be a start. I guess your field of medicine will be a huge headache because of the sheer complexity and number of terms. You're going to need a massive data set to do it right. Unless you want something more generic like a document classifier, it's more looks at the words in general, that would work quite well. The more detailed the more vague your problem becomes and the more options there are. For example, grammar is a good thing. If you say, I want homophones, the 2 and the 2 problem with 1 or 2 O's. If that's all you need, 2 or 2, you're probably gonna need 100 sentences.
No, you don't. I had 10 for each.
10, even better.
Booyah.
And it will come up with the right prediction. But that's not the only homophone. You got access and access. I have access or access to the healthcare area. That's not the same access. There's a different words. It sounds the same.
I had 10 for, so the reason why I asked you this question is loaded. Because I did it with single words, like we did the simple ones. 2 actually did more than 10 sentences because like that contextually, but like access and excess, by the way, Grammarly doesn't do this either. And so we were able to detect whether the word was incorrect in that context because you could make a sentence with both and it would sing right. But in a research tool, in a business tool, you know that they're very different concepts. So we had 10, but now I'm building the logic errors. We call it informal logic, logical fallacies. And I have words that I'm trying to detect within a pattern, like some, all, this is all based on quantification. So I'm able to now look at keywords, like some, all, but I have to have all those in one line, and I have to have a form, a logical form in which they must all be set up. So that's how we're building our logical fallacies tool, which no other company in the world has built. Why? Because we've used a combination of BERT and Spacey. We're trying to see which one works better so that you can look at the location of the words and the use of the words within the context of the environment.
And that's an excellent example of why the demand for state-of-the-art models is there, because you can do new stuff with it. Stuff you just couldn't do with the old algorithms now becomes possibilities. And of course, every company and, well, government agency, research facility is very interested in that. Hey, we need somebody who knows these models, these state-of-the-art models, so they can develop a new application for us. Okay, well, here we go to a different subject. Are there any questions about the whole AI deep learning? No questions. Copy that clear. Very well. On to semantic search. It's an application I recently worked on. It's kind of my darling now. Semantic search basically means you need to look at the meaning of words in your search phrase, an utterance they call it in the chatbot world, because the user, you never know really how they're going to phrase their statements. And it was still doable in text in Google search. You type something that's not too long because you don't want to keep typing and get to the point quickly. But if you have a voice assistant, you can just ramble on. Oh, Siri, I'm kind of looking for a hamburger place. No, wait, make that a pizza parlor near me. That's what Rotterdam Centrum here. And it becomes very hard to detect what does this user mean. Okay, pizza place, restaurant, center of Rotterdam, that kind of thing. So, for my application, it's a bit more simple. I need a semantic search for my database. So the student can look for terms in one search engine, like Google, you type it in one place, not in different places. If you want articles or you want definitions or you want something, you're not going to use different searches. You want one search that searches everything. So the things that a user in my case could use is, I need a scholarly definition of accounting standards, or all research articles of Professor Jensen, or the best quotes of Elon Musk, or what are synonyms for capitalism. So what are these semantic search used for? Well, Google search, of course, you can type in whatever you like, and it's really good at picking up what your intent was, what you're actually searching for. Chatbots, they have the same problems. They need to know what is the user, well, typing or talking about. And a voice control assistant, same thing. You just talk to your Siri or your Alexa. Alexa, can you dim the lights and turn Netflix on with that and that movie? And it might do so if everything's connected. So how do they do that? No, not that fast. It can be split in two things you need to do. First of all, you need to get to know what does the user mean. It's called intent. What is the intent of the user? If I say, I need a scholarly definition of accounting standards, then he wants research, he wants a definition. So I'm gonna look in my definition database, not in my research articles or my quotes or my acronyms. This guy clearly wants a definition. If I say the best quotes of Elon Musk, then it's simply the quotes. You know, the man said wacky things, some inspirational, some odd, but you get a few good quotes of that guy. If I would say, give me a research article of, or I guess on Elon Musk, and I don't believe he wrote research articles himself, but there might be research articles that talk about Elon Musk. So then you need to search the article database, not the quote database. It becomes a bit more difficult when you don't give your intent away in your search. If you just say Elon Musk, okay, there he is, what to do with this guy. So you just add a lot of words in there that kind of clarify intent. If it's accounting standards, you probably want a definition. If it's Professor Jensen, you probably want research articles. If it's George Washington, you probably want quotes. It doesn't work perfectly, but as long as there are hints like synonyms, quotes, or what is, or define, then it's almost 100% accuracy of the right intent. So here's how I trained that. It's again the structured data set. I came up with, well, all possible things the user would type in there, and I simply defined it, a quote, a definition, a citation, etc. So it knows what to search for. I split it for 90-10%. We tokenize it, we pad it, we vectorize it, and on it goes through my GPE, and out comes the following. So at the first epoch, you see a loss training, and then the validation is what I'm really looking at. It's 70, 73. It got really accurate at the end, this one, like 97, since again, the problem is contained. You see the sentences, they're really short and simple, so it's much easier to, well, make a prediction on that. What's the difference here? The training loss is how the model during training makes these predictions, and the whole purpose of the training is to minimize the training loss. That's all it really is instructed to do. The rest it all decides for itself. So it's a whole big black box model where I simply say, this is an input with labels and sentences. Minimize the training loss, please, and so it does. But then you get a process called overfitting. Like it gets to see the patterns, but only for the specific data set you gave it. It knows more and more about that. It starts to see patterns where it shouldn't. It's called the noise and signal theory. Think about the stock market price. It scatters all over the place. In short term, it's all noise, but in long term, you see a much smoother flow. Be it as it may, it needs to minimize the training loss, which is simply, it's not an accuracy, but it's how close are the predictions and the real labels together. So how accurate, not accurate, but how close. It can make mistakes, but economy and finance are much closer together than something very unrelated. Well, with validation, that's at the end our little extra set. We test simply at the output. We look, is the predicted label the same as the actual label? How do these two, they're similar but not the same. The point is the loss means the distance between the true and predicted value. It tries to minimize those. Doesn't say they're the same. Well, the accuracy means as much as the same as possible. For example, if I have a very low training loss, I minimalize everything, the error and the real come close together. But if I still have a low accuracy, I made a lot of very little mistakes, very little nuances. That the training loss is very low, yet the accuracy is still poor. The other way around, I can get a poor training loss, a high number, but my accuracy is still very high. It's 70 or 80 or 90. What happened then? It's the opposite. I made a few big mistakes, but not many. Most sentences are okay, but a few are completely off. So it's good if you dive into these models. These are the two things you need to monitor. But I guess that's beyond the scope of this specific lecturing. Okay, so how did we do it? In goes the sentence. What is monetary policy? Again, tokenizing. Padding, by the way, is a term I haven't introduced. It's BERT and many AI models expect a fixed length input. If I say my max length is 64, it expects 64 words, no more, no less than 64. So if I have less than 64, I use padding. I basically add 0 words after it. If I have too many words, I simply cut it off after 64, but it needs to have 64 exactly if I define it to be 64.
Erwin, can you go back to why you think that we've had this debate back and forth of why 64 words? We've tried, sometimes we're like, oh, our data set's pretty bad, and why are we getting such a low accuracy? Is it because when it's cutting off at 64, the kind of the relationships or the connections, you know, between the words? And then we realized like 64 is ideal. And this is so embarrassing to say, but it wasn't about the padding, the numbering, and all these things. You have to be very careful with your data set, like Erwin said, because sometimes if you make your data set, you have to build a data set, right? You as a human being who's not very good at debugging all the time and finding things, your eyes get tired of generating all these sentences and these documents, you end up making flaws within the data set itself. And so it's nothing to do with your numbers in your sentence. It has nothing to do with the padding. It has to do with you. So often, if you know you get to a point where like, why is my accuracy so low? Always go back to your data. So it has nothing to do with padding, your tokenization, your vectorization, any of that you may mess up. You personally screwed up on your data set.
Most data sets get any model, including birds, running pretty quickly. If you test it a few times and you have your errors out, in a week you get it running pretty well. Then it's all about the data set that makes the difference. That's where the hard work is. Anyway, so we got our sentence, like the user wants to know what is monetary policy. We need to make a prediction. Out comes again the categories. Well, the first one is the biggest number, so we label it definition. The intent of the user is to find a definition. Then we run it through our Spatie tools because we have the intent, we want the definition, but what do we want to define? Well, for the human, it's obviously monetary policy. So first, I don't know that. The computer doesn't know that. So my first attempt is named entity recognition. That is your people, your places, your amounts, your dates. It's got nothing on here. So, okay, that's ignored. The second one, it's my Spatie matcher, which gets my taxonomy of business terms. See if anything is in there, and well, it did find monetary policy. So now we know the intent, find the definition, and we know what to do about monetary policy. So now simply, I shoot a query to my database, to the definitions table with the keyword find definitions of monetary policy. If I would have the document classifier already classified the document, I can add in the field of finance primarily, for example. And then out comes something like actions taken by the Board of Governors of the Federal Reserve System to influence the money supply of interest rates. Well, that seems about correct.
And we have like 20 definitions generally with all our data sets, like our definitions, same with quotes. And it's very wise if you want to build your own data set and you want to build like a semantic search tool, you've got to have a lot of, you have to spit out recommendations more than a few. You got to give the user enough to work with. So that's an important one.
Okay, so on to the last subject. It's not that much time left anyway. Chatbots. It's kind of the thing where all these theories I explained today come together. Maybe you know the Ex
We
Machina
watched that
movie.
last night.
It's a great movie. It's a movie about does anybody know the Turing test?
Sure.
It's for the people who don't know, it's a test a person would do to see does he know whether he's talking to a computer or not. If the language is so fluent, well, I guess you can't give it away by showing a robot like that, but I've seen an example from Google where they have a chatbot with a complete natural voice. They even add things like in there now and then to make it human-like. It can, for example, it can be personal assistant. It calls the hairdresser. I'd like to make an appointment for a client of mine, 12 o'clock. Yes, she's female. Let's see, do we have anything after 12? No. Oh, I have to call you back. Wait a minute. It's very, well, it will definitely pass the Turing test because you know it's a chatbot because you click on the video, Google chatbot, sounds realistic. But if you wouldn't know the person, the hairdresser on the other line would have never guessed. So that's kind of the thing with the chatbot. A chatbot, it's called conversational AI. It must know the user's intent and it must know what exactly elements you're talking about. And then it must give you back a natural response that you actually think you're talking to a human. So where do we start with that? It's a combination of intent, which is often a BERT model, and things like extracting the keywords with Spatie matcher and Spatie named entity recognition. But for example, I have a chatbot and I'm saying, I'm hungry, I want to eat a burger, find a restaurant near me. Intent is find restaurants, and you can extract things like burger, restaurants near me, and maybe you have the GPS location of his phone so you can know, oh, he's at the center of Rotterdam. A reply would be finding a list of hamburger restaurants in the center of Rotterdam, and then you search the internet and you copy it, you get your links. A lot of it is links through social media to Facebook. Everybody, like burger restaurants are probably on Facebook, and you can just get the information from there and make a reservation through there. Yeah. But so far so good. It sounds a bit like semantic search, as in I have something I want and out comes a reaction. But a chatbot needs a lot more than that, because a chatbot is actually conversation, not just one sentence that needs to be analyzed. It's the kind of the core of it, the semantic search. But let's see what else is there. First of all, your speech to text, which already is a problem, because a lot of speech to text, you can get it right, but it needs to train on your voice and your specifics. If you talk really clearly, it might work out of the box, but if you mumble a bit or you have a weird accent, or it can, well, it needs some training time to familiar yourself to your voice. And I guess chatbot doesn't have that time, and it needs to deal with everybody. So speech to text is already, well, can you get his speech to text? Then the part, the conversational NLU, that's a natural language understanding. It's basically what we did with semantic search. It's knowing what a sentence is about, what the intent of the user is, what exact details he needs. Then we run that through a dialogue manager, because, as I said, a semantic search is one sentence at a time, and I don't really care what the previous search was about. I just look at this sentence, so it's not that hard. But here, 10 sentences down the road, I need, let's say I'm in health insurance, and he said, he was already insured at the competitor. Do I need to cancel your insurance maybe before I start a new one? You need to remember things that are said previously. And well, this one actually, I still don't know how they do it exactly, the answer generator. You need to give a proper answer, and generating text, well, you can choose from predefined sentences where you just put a variable in it for the name or the place, that works fine. But to properly come up with new text by the AI remains a challenge. And then at the end, we need to get that answer back to text-to-speech generator. That's probably the easiest step. They've got pretty good voices by now. It's a pretty standard procedure. Eventually, you can hook this up. Usually, you use interfaces like Messenger, Facebook, Instagram, WhatsApp. That doesn't really matter which one. It's good for going back and forth between you and the chatbots, and it also can make connections underneath. It can search things on Google. It can like try to make a reservation at the hairdresser or the hamburger place. So they got here. It's a kind of an example. Oh, hey there, my name is Sarah. So you immediately get an intent is agreed. It's an introduction of a user. What do we get out of there? Well, her name is Sarah. That's kind of all we got from that one. Then she probably says something for us. It says to order a pizza, just tell us which kind you like. She probably says something in between. I would like to order a pizza. I'm hungry. So now we know its intent is order something, order foods. We know it's pizza, and we can make connections through Facebook to pizza places in the area. You can copy its menu, paste it here. Then the user can say, I like the pizza calzone, and back goes another connection to the restaurant. The order is there electronically. The cook starts cooking the thing is shipped. I guess there's a payment thing in the background too you need to work out. So yeah, there's a lot extra beyond just understanding the utterance of the user. That is the part I know best, but yeah, the chatbot is a lot more complex than I thought at first. At first I thought I'm gonna make one for Gailo, because once we get the product out there, I'm not gonna train a whole help desk, pay for that. I'm just gonna make a chatbot, and people can deal with that. Now I realize it's a lot harder.
But there's those that you can use from Azure, right?
Correct. There, of course, I'm not the first one who thinks he's gonna need a chatbot. So you got several options. This one I like. It's called Rasa. It's an open source chatbot. It works in Python. You can quickly download it all for free. You get it running on Python with their, how to say it, simple dictionary with intent and the manager, the conversation manager and such. You just like anything in Python, you get it out of the box running quite quickly, but you can get birds running out of the box quite quickly. You can get anything running out of the box quickly, but the point is to get it running on your data, so it gives the response you want, and make the connections you need, and the conversational manager needs to be so. That's a lot more work, but at least you got all the technique is underlaying there. It's very similar to what I explained usually.
So give us an example of like how you've thought of building our chatbot. Like,
Well, I thought I'm gonna create a bird model for the intent. I can extract what the user, the named entities. Then I know what it's about. But then dialogue manager and generating response text. It's all a lot more difficult. So I'm not gonna develop it myself. That's gonna be a massive
intern, you
project.
wanna do it? As an intern,
No.
I'm just kidding.
I'm not sure if you're familiar with it, but isn't this the same as FCOEM?
I don't know that one.
Tell us more.
It's from Marco Bobbin, it's verbalizing statements into data sets. So this should be an example.
Yes, it can be a part of that, yes.
But,
Could you just we'll write it down.
Of course, Rasa is not the only one. For example, I looked at Azure. You got a thing there. First of all, you got the Azure bots, where you create kind of autonomous working software. Think about like a bot, but also like a chat bot, which is a sort of, bot by itself. So the bot service is kind of, it creates the environment. The bot service provides the infrastructure. You host your bot there, your services. It has connectors to social media and whatnot. Then the second thing you need is Microsoft Cognitive Services. It's another program running in Azure. It's basically the eyes and the ears of your bot. You can do all kinds of things, natural language processing. If you have a chatbot, you can use computer vision if you need to see something. For example, let's say you're Boston Dynamics and you want to have these wacky robot dogs that can dance and backflips and whatnot. You're going to need a lot of these kind of things. The thing itself is a bot, but you need eyes on there. You probably need hearing detection. You need a position. You need so many sensory inputs to have it running like that. So that is comparatively to this. The bot is kind of the software or the hardware package that you run. And the cognitive service provides the sensory input and output. It's the mouth of your bot, it's the eyes, it's the ears. And then a specific part of the cognitive service would be LUIS, the language understanding. It's the kind of cloud-based AI solution of Microsoft to tackle these kind of problems, to understand the utterances of the user, to generate the response text. So with these three elements, you can run a chatbot too. The thing is, Microsoft claims you can get this thing running in 15 minutes. It's a generic version with all pre-trained models, pre-trained responses and whatnot. Maybe they're right, I don't know, I haven't tried it in Azure. Gonna cost you. Microsoft Azure is not cheap. What is cheap is Rasa. There's open source, which is absolutely free. Well, you get no support for that and all, and that is a bit of a problem. I talked to a guy at a big Dutch health insurance who was working with chatbots, and he said something like, "Yeah, I love Rasa. We were really excited about that, but the management said no. You're going to use Azure because we have contracts with Microsoft and support and." If things go wrong, we call Microsoft and they send their best AI engineer to fix it. Well, with Rasa, you got nothing. It's freeware, But said, well, it's just as reliable. Yeah, be it as it no, they said, no, we can't do it. We don't use freeware in, critical systems. So there are more things to consider what system to use. I think that is the end of the presentation.
Perfect timing.
Wonderful.
Thank you.
So, how are people online? Any questions about NLP, I guess? I guess it's been quite a long since. One question?
We have one question.
I also heard about bird time. So birds and bird time was a different thing.
There's lots of birds.
There are many varieties. I'm not familiar with birds. I think I've heard of it. But the thing is, almost anybody kind of did the fine-tuning to develop a bird model for their own environment.
Okay.
I heard of a guy in student at the TU Delft, and he worked with a BERT model to look at DNA sequencing. Because it's similar to word sequence, you know, you have a lot of it. The order is somewhat relevant, but not completely. And so you could apparently develop the BERT model by fine-tuning the final layer to become a DNA sequence tool.
There's a lot of BERT models, like we're gonna do next sentence prediction with our continuity feature, and Grammarly does do that, I have to admit. But there are so many, like if you look at GitHub, Spacey again does it. We tried to work with one which was Spacey BERT for spell checker, and we're building our own instead because it was not very good. So if you look at third parties, a lot of third parties use BERT as the foundational, and then they build their own. So you got to be very wary. You go to GitHub and you go, oh, I can tweak